Right. One good news is actually I was about to drop you all an email for the portal that I was working for the portal that I was working on to give you guys access to it. Like I'm running low on Google Drive space. So I've just converged upon using Vimeo to host all the lessons and all. This way you can stream it on any resolution needed. It would do transcoding and all. And plus it would keep videos private as well. I've just completed coding the portal, was just doing a final round of testing before I drop you all an email. So most probably by tomorrow, if I spend good amount of time testing tonight, then most probably tomorrow onwards you'll have access to that portal. And I'll stop uploading things to Google Drive, and on that portal, so basically on that portal you'll have lifetime access to all the content that we have. And basically I've automated almost all the stuff that I wanted to manage a course like this. So yeah, I've done a lot of hacking lately. I've tried to I've tried to set up a separate entity around it called Relog, wherein I'll upload all the advanced courses, this being one. This would be my flagship. Other thing, like I'm planning to do one on database internals, one on Git internals, uh, then might be on generative art, one course. But obviously those won't be, but basically those won't be code based, but self-paced course and something. And yeah, I have few very interesting plans around this cohort. Like our engagement should not be just restrained within this 2 month span, but it should go all along, uh, basically till the time we exist, right? So that is where I'm planning to have guest sessions once a month. Uh, it's still in the roadmap. I'm still trying to get my first 5 speakers to get the ball rolling, so that like we always have something to look forward to if you are being part of this squad. So that's something that I have in mind, but still I'm just trying to converge upon few things that I can handle myself, and just basically getting help from some of my friends to drive some of the other things around that. There are a lot of interesting things on plate in progress. I never thought that I would be running third board. So yeah, thanks for enrolling and joining. Really happy. Chala. It's 4 o'clock. This week, as you might have received the agenda email, this week what we'll be doing is we'll be diving into distributed systems today, and we'll be seeing ID generation tomorrow. Right. So with respect to distributed systems, like this is the core of any system design, right? So we have seen like so almost every so the most skipped subject, or the most simple, or one subject during our CS curriculum which we never paid a lot of attention to, has to be distributed systems, right? We were interested in DBMS, OS, data source algorithms, obviously, and languages courses, maybe compiler to some extent, but distributed systems was something that at least a lot of folks that I know, and including myself, was something that I was like, why? Who does that? I have one local machine, one server. I'm able to make calls and like do things. And why to study this part? Wala? But now, once we are into industry, once we know that when you are building things, it has to be, if it wants to be scalable, it has to be distributed. And so that is where our whole focus for today's lecture would be to understand how to build distributed systems. So it will be very less theory and a lot more things that we'll be doing into it. So what we'll be doing is like just to cover and basically just to bring everyone to the same line. I'll just spend like 5 to 10 minutes, and then we'll immediately jump into system design part of it. Right. So in general, for distributed system, a basic understanding of this is a distributed system has multiple components which runs on multiple machines, right? If all of the components are running on the same machine, then it is obviously not a distributed system. And since everything is local, the communication is lightning fast because it doesn't have to go over the network or something. So then it is typically not a distributed system, because that's where the challenges of distributed systems comes in, where you have like a lot of machines, a lot of interactions, and like so many things happening here and there. that clock goes out of sync and your network becomes slow or your network is partitioned and whatnot, right? So those challenges occur when you have multiple machines where actual Ethernet cable breaks and basically shit happens here and there. So when you are building something that is horizontally scalable, you would have to have multiple machines of it running. So that is where the communication and coordination part of it comes into the picture. Like last week when we were discussing the ordering of the messages, how would that be? That's basically coordination. Like how would you coordinate if an event on the same key, well, like how will you order events or how will you order messages or how will you coordinate that only one of them executes? Like let's say you're building SQS consumers, how will you ensure that only one consumer can access a message at a time while others are waiting for it, right? So, something similar. So if you are doing something like this, how will you ensure the communication coordination of it? That is really challenging. So even though you have multiple components, different machines, when looked at from a bird's eye view, it solves just one purpose, right? So depending on the system you're designing, it looks like a single coherent system where you'd say, okay, this system is nothing but my medium block. Like internally, it might have 50 different services, but for for a uh, for a really high bird's eye view, it just looks like one system which is there. It's like medium.com. Like that's the beauty of it. So you have to make it look like a single coherent system, even though you might have a plethora of microservices running behind the system. Now, the interesting part of the distributed systems comes in when components starts to fail, right? When components fail, typically what happens is in a poorly designed distributed system, when one component fails, it leads to failures of other components, which seemed unrelated, but they fail in cascade. Like one fails then another. So it becomes like the domino chip falling, where you push one and it leads to basically falling of all other chips one after another. That's exactly what happens in a poorly designed distributed system. Right. A very simple example of this is you have like hundreds of microservices, each service calling, let's say your main profile service. That profile service has a database. That database choked, like due to high number of requests. So that database become a bottleneck. Then because of that, it started having a very high response time. So the latency increased a lot. It had a cascading effect on the API server or on the API servers of this profile service that were making call to the database. Now this API started taking a lot of time to respond. Now this API was consumed by a bunch of asynchronous workers and a bunch of elements from other services. Like so now those started experiencing high response time. Now the consumers of those services would also get affected, right? So this is what a cascading failure looks like. Like although it seemed like I never used the term fail, it was like high response time. But once this high response time or once all the requests start queuing up in the system, it would lead to your system crashes or your process crashes because your process or your machine's memory would be too less to handle that much of thing, and your machines start crashing, your pods start crashing, your containers break, and whatnot happens. Right. So this sort of cascading failures is something that you should be protecting your systems against. Now, a good distributed system always implements something called as a circuit breaker. How many of you have heard of circuit breaker? Varun, would you mind explaining it in 1 or 2 lines?
Yeah, I mean, basically the concept is, let's say there are the failures are happening at a very high rate. Instead of causing the failure to happen at the end, just make the request fail immediately. Basically, instead of doing the processing or waiting for the database to respond, the last, let's say, 1,000 queries are timing out. Maybe it's better to not load the system more and actually say that, okay, I'm not going to process your request because anyway it's going to time out.
Okay, great example. So that's exactly what circuit breaking is. So what happens is with circuit breaking, as basically very well explained by Varun, what exactly happens is, let's say you are making call to a certain API. Let's say I am the service of communication, and I'm making call to Jobo profile API, and that profile API is talking to the profile database to get that information. Now let's say profile database choked, because of which profile API started taking a lot of time to respond. Now, because of which there was a back pressure on my communications API. Now, when my communication API was making a call to profile API, I know that that API, that my profile services is performing really bad. So if I make that call, it would it would add more pressure to the system. Now, what I would really want is my communication API to not make call to API and just either use, basically depending on the case, I would have to stop processing messages if I'm a communication system, or if I'm a real-time system, I might have something configured where if my payment, if my profile service is down, what do I need to do? Like that particular handler should kick in. Now, what would happen is you would have a flag, right? Some flag that denotes that instead of making a call to profile API, do this other behavior instead. Maybe use a dummy response. Maybe not call that API. Maybe don't process the message. So you are breaking the circuit so that you definitely know that if you were to call the API of profile service, your system is going to fail, or that API call is going to fail. So you are breaking the circuit, right? And which leads to not which leads to breakage of the chain. Like basically the domino is actually continuously falling, and you are breaking the circuit, which means which message do तीन domino you remove from the basically from the sequence, which means other dominoes would remain intact. Now, what would the behavior of those dominoes or of those service would be? It would be totally dependent on what kind of things that service would have to do if it did not get response from the API service, right? Or the dependent service. So this is something that is very specific to the business logic that that particular service handles. But the idea remains the same. Circuit breaking, implying that if I know my system is down, I would not, or I should not be calling APIs of other system because it would anyway fail. And if I'm making unnecessary calls, now let's say a great, now you would ask you why to even do that, because I know my service would fail. Let the system fail, what would happen? A great thing could be like, I know that my replication lag is high, and my replication lag is high, and if I have a circuit breaker in place, I can basically turn on my circuit breaker, which means my no call to my API service going on of that service. So which means no load on the database, which means no queries on the database, which means my replication, that is my database, is getting a chance to basically catch up with the master. Right? Basically, this is a very simple example. Like you don't want to have a lot more load on the database which is already struggling. Right? Number one. Number two, let's say you are waiting for all the connections to drain before you do that restart, so that any of the in-flight requests are not affected. Right? So you would want all the connections to drain up, and that's when you would take some destructive action. Let's say a machine reboot, API server reboot, deployment, database snapshot, and whatnot. If you want to have a behavior like this, that's when circuit breaker would enable you to ensure that no new requests are being forwarded there. And you would just monitor that, okay, now all the connections are drained off, and now I will take my destructive action. Right? Something similar to this. So this is where circuit breaker plays a really, really important part in your infrastructure. Right? Now, why distributed system? Again, as I was saying, horizontally scalable, because a system is not really scalable if it is not horizontally scalable, because vertical scaling has limit. But a disadvantage of this is higher latency, because now instead of getting, like, let's say you have a monolith, instead of getting it from the one or like a few set of machines, you would have to do so many inter-service communication. Like, and each inter-service communication is nothing but a network call. Each network call means added more addition to the response time of that service, right? So the overall response time always shoots up when you transition from a monolithic application to a microservice based application, because now a lot of things has to go over network, and now obviously networks are not reliable, retries might be required, other system might be overwhelmed. There are so many cases to handle, but that is really essential to do so. Then comes why distributed system. A second point, reliability, because since you have multiple servers handling, even though a few servers go down, other servers can take up the load. You can add more servers to it to handle the load, right? Then comes performance. With distributed system, you get great performance because it's horizontally scalable. Vertical scaling has a limit. Horizontal scaling theoretically has no limit, which means you can have a much farther scale to handle as compared to vertically scaled system. But another disadvantage of distributed system is observability, because when you have like if you had like 5-10 servers, it was easy to monitor. But when you have thousands of servers, how would the entire monitoring thing work? That becomes a little tricky, right? How would your system monitor? You'd need to monitor CPU, memory, and whatnot metrics of the system, inter-service metrics, communication metrics, network base, alarms, whatnot. So observability is something, and so latency and observability is typically the two major drawbacks of having a distributed system. But with time, if you solve that problem, or if you are okay with higher latency, you might have its own set of optimizations to reduce it. But with observability, if you do it well, you'd be more happy than you'd be more happy using a distributed system. Few of the fundamental problems of any distributed system is consensus. This comes in very handy when you have a setup like a multi-master setup, or when you have not really multi-master, but a setup wherein someone can be promoted to a master something. Like, let's say you have a cluster of database nodes, and typically one of the nodes, and let's say master is taking all the writes, and there is one, and basically there are 50-60 replicas, for example. And let's say if master crashed, who takes the place of this master? Like, this is where the consensus happens, where all other 49 nodes would vote and would agree, okay, this server is the new master, so all the rights should go to this particular server. This is consensus for who becoming the master. Another consensus is with respect to data integrity. Like 4 of the machines say that my value of X is 4, while 5 of the machines says my value of X is 7. Right. So in that case, who would be majority? So all the machines have to have that consensus. See, what's the true value of X? Right. So there are consensus algorithms, which are basically protocols through which you can have achieve consensus in a distributed systems. This seems far-fetched, but it is very much in reality at scale. Even when you hit, let's say, 10,000 requests per second, all of these problems that we have studied theoretically starts to kick in some capacity. Might be a smaller thing, but as and when you would scale, you would always come into the problem of consensus, clock synchronization, leader election, distributed deadlocks. All of these problems do kick in, right? So be wary of the fact. Now, a key to a good distributed system, like one rule of thumb to designing a good distributed system is like assume every single thing could fail. Like if I'm making a call to a profile service, I would assume that my profile service is giving me a lot of high response time. So I need to have a request timeout for my API call, right? So that if that gives a very high timeout, but still I would be within my SLA, right? What if that service is not available and I'm not getting any response? So what should be my default response to my dependent systems? Right? You should always ensure, or you should always think about every single component that you have, or every single API call that you are making, or database call or cache call, anything would fail. What would you do to avoid that? That is where the robustness comes into the picture. So how would you make your system robust? So typically, a good distributed system is robust, is available, is durable. Right? So if you are doing that, you would always have to assume that every single call that you are making is failing. And what would do, and basically what would you do when it fails? Either retry or don't process the request or throw an error to the user, depending on the kind of business logic that you're doing. One thing to keep in mind is when you're doing this, another advice would be like take baby steps while building any system. Like just go like one step at a time. Don't give too much responsibility to one of the basically one of the components of the system. Take baby steps. See what would happen if this message did not ever reach to my intended server. What would I get? Like always think of this like really teeny tiny baby steps when you're building any distributed system. This would like help you build a really robust and highly available distributed system with ease, like assuming every single thing would fail and taking baby steps while designing. Right? So before we jump into load balancer, any questions? Yeah, Umang?
I had this one doubt. So basically,
Hmm.
monolith can also be distributed, right? Or is it only in case of microservices that
No,
distribute?
monolith is this. Malab, with respect to you, you can't have just one API server running. If you have enough scale, you would have multiple API servers. But typically, the business logic is not split. Like you are not having multiple services running. Like there is just one process running,
Hmm.
which may be running across like 5-10 servers. But typically, those are all identical servers.
Okay,
Right?
so
Kahin pe bhi there is no inter-service communication happening.
okay, so like microservices automatically become distributed, but in case of monolith, it becomes distributed
It's more like having multiple API servers running for you.
Okay,
Running that same piece of code. So business logic is there in just one repo or in just one process.
got it.
Yeah, Vishal?
Yeah, so would you be able to brief us more on how you have used circuit breaker in your projects?
We'll take that at the end. Malab, just do remind me. I'll share those experiences at the end. See how we built a service, how we built a circuit breaker and implemented it in our use case. So I built it twice up till now. So yeah, I'll share my experience on that. Okay. So now what we'll do is something that we have like very heavily used in systems that we have designed till now, like load balancers. Like whenever we think about it, the first box we draw in any system design, like first is the user ka icon, like one circle, one line, tick, tick, tick. With the second, but then the next immediate thing that we draw is like one box written load balancer, and then we put like 4 or 5 boxes behind it. Like now, this is something that we have inherently used, which says that okay, now if I would want to scale it, I want to make things horizontally scalable. So I did multiple API servers, but I can't have like my clients cannot have addresses of all the API servers. My client needs address of one machine, and that machine can see wherever I would want to forward the request to. So that is where the load balancer kicks in. So you have customers like you have basically clients C1, C2, C3, C4. They are all making calls to this one API load balancer's endpoint. This API load balancer internally has like 3 massive servers running, server 1, server 2, server 3. Depending on where the request or depending on the scheduling logic, we would pick either round robin or like least connections. Basically, there are so many algorithms to what that works on. So let's say it works on some hash key based thing. So depending on what the user ID is, the request would be forwarded to a certain server. And so this is something that load balancer gives us. And this is typically why we have been able to scale systems. If load balancers would not have been there, it would be almost peer-to-peer network, which was really hard to scale, right? Because how would you like you don't have a single authority to point to, you would always need to do multiple hops to have that connection set up. So that is really tricky to have. So load balancers is typically why we have been able to build great systems out of it. So because that's the one irreplaceable component in our system, right? So this thing with respect to load balancer, a great advantage that you get is like you prevent single point of failure, because now instead of the customer directly connecting to like your one API server or hitting your one API server, with load balancer you are having 3 behind it. So even if one of the server goes down for some time until another server is spun up, the other 2 servers can take up the load. So you don't have a single point of failure because other requests are still serving. The point you have single point of failure in the system, you have designed a very bad system, right? So you always have to ensure that the system that you're designing does not have any single point of failure or any overclocked server, which means overloaded server due to request or something. So load balancer, as in the name suggests, it balances the load across multiple systems. So it would handle that part. So there are several places where you can place load balancer, like any place that but you can think of it like any place that abstracts identical systems. Like this is a critical point where you would have to abstract identical systems. So here the 3 servers, server 1, server 2, server 3, they have the same piece of code running. So no matter where the request goes to, it would be serving the request in the same capacity, giving the same set of response. So server 1, server 2, server 3, with respect to the code base that it are running or the business logic that they are running, or the functionalities that it is giving, it will be running the identical thing. So typically load balancer does not differentiate between the types of servers that it has. It just gets the request and it just forwards it to any one of the server depending on the configured algorithm. So this is an important part. So where you can place it anywhere in your system where you see multiple identical systems and you would want to, you would want to balance the load there. So one example is like you may have an external facing or an external load balancer that everyone from the internet connects to, and it all the request comes there, and from there it basically enters your VPC. Yeah, basically it enters your ecosystem. And so that is an external facing load balancer, typically an internet facing load balancer. Another is, oh sorry, internet facing load balancer. Another is internal load balancer, which means the load balancer that sits within your infrastructure, typically in front of multiple API servers of your internal microservice. Right, so that is one way. That is another example of load balancer where you can like put the load balancer. Now within VPCs, like where would you do it? Like you would want to load balance across your API servers, maybe databases, or maybe cache. A great example of an internal load balancer for database use case is MySQL Aurora, a managed offering by AWS. So AWS has forked MySQL repo, and it has given like, and it has added a lot of cool features on that thing. And one of the great features that MySQL Aurora gives you is, read replicas by abstraction. So you have one primary database, you have multiple read replicas. So what MySQL Aurora, so this take writes, reads, and typically this is what the sync happens. Right, so all the read requests go, all the requests go here. And then if it is read, it is forwarded. Your API server, no, this is the wrong way to put it. Just give me a minute. So what would happen is your API servers would be connected to, you have one write database and couple of read replicas. So your API server typically creates connections with all the databases. So your read replicas, your write database, anything, and depending on the request that it is getting, it would either connect to one of the database and make a query there. Now what Apache Aurora did was, Apache Aurora, like if you see with read replica, now let's say you would have to scale up a read replica, or you would want to add one more read replica to it. So you would have to change the configuration and let API server create connections to that read replica as well. Right. So if I would want to scale up or scale down the system at will, or the read replicas at will, it's a very tedious thing. So what AWS folks did was, in the Aurora offering of theirs, what they did was they added a read endpoint to every database and one write endpoint. So you would have an architecture similar to this. Instead of having this, what they've gone for is this RLB. So this is a read load balancer. So they would, and internally it would forward this to this. So they've added one abstraction in front of their read replicas. So all the requests goes to this read endpoint, and this read endpoint internally forwards the request to any of the configured read replicas. So now you can scale up or scale down read replicas at will. So this is a great example of internal load balancer put in front of a database to, to give us ability to horizontally scale the database. Right, similar, and you can obviously build this thing without using Aurora, like using Route 53 or any DNS offering. You can like very easily configure it. So it's not hard to configure, but this is something that comes out of the box if you are using Amazon Aurora or MySQL Aurora. So, but if you want to implement it, just go to Route 53 and see how you can do it. It's a very simple trick that you can apply. And similar thing you can do with cache. There is no rocket science behind it. So it's again a really very simple thing. It just about, it gives us that flexibility to, scale up our databases, scale up our cache at will. Right now, there are typically types of load balancers like software load balancer, hardware load balancer, L4, L7. Like there are ton of material available on the internet. कि मतलब what exactly that is. But to give you a very small gist, software load balancer is typically when on the software side of things you are doing load balancer. Typical Nginx or HA proxy is an example of this, where you don't have a physical load balancer as such, but it's a software load balancer wherein you're configuring key forward the traffic to this server, or this server. So these are my configured backend, forward the request to it, and it is just an application running. Right. There are hardware load balancers which are nothing but physical machines on which other machines are actually physically connected. Right? Those are hardware load balancers. Like, to be fair, Amazon managed load balancers or any load balancers that you see is typically a hybrid between the two, because in some cases you might get a dedicated machine. Like, basically this is still theoretical, but at the end the usage is how like you would be using it to like serve your use case. So don't really worry about that part. So hardware load balancer, it is a physical machine on which you could find like multiple physical other servers being connected to, and you are basically throwing requests here and there. Then L4 and L7 load balancers in the OSI stack. L4 and L7. L7 is the application level. L4 is the session layer, network layer. No, sorry, L4 is the L4 is
IP.
the transport layer. So it works on the so either on the transport layer or on the application layer. So this is a classical example of like L4 versus L7. So a load balancer can operate at L4 or L7. So now what happens if a load balancer is acting on L4? It means that it would not have any information above that level, which means L5, L6, L7. So session protocol or application protocol, it would not have any information. So it like, for example, something operating at L4 would be something who only knows TCP packets. It would not know that it is an HTTP thing. So it would not have access to HTTP headers. Like if you have used Nginx as a load balancer, you would have configured it like if the header is this, do this thing, or for example, pick the user ID from the header and then forward the request to a certain server. Like that is L7 software load balancer, which has access to the L7 data, which means application data. Right. L4 load balancer on the other hand works on like raw TCP packets, like be it TCP or UDP. It would just do load balancing. It would not care कि क्या है. It would see कि TCP connection hai. I would have a few of my servers configured, and I would just connect to another database or another backend server and just basically forward a request to one of them. So this is a typical differentiation between L4 and L7. Most of the load balancers that we use right now are typically L7 load balancers if you are running it yourself. L4 load balancers are typically something that you would normally not use it, but because it is like balancing on top of raw TCP connection. So it would have no information apart from like till L1, L2, L3, L4 layer tak. It would have information, but none of the application related stuff. So L5, so basically session, presentation, and application. This three layers information it would not have, right? So we typically don't really have a lot of choice if you are cloud native to use one or the other, but we can treat them as one, but we'll see to implement one, how we can implement a load balancer in some time, right? Okay. Just to cover a few things before we jump into the system design part of it. The algorithms of load balancer, like this is how your load balancer would decide to whom should I forward my request to, right? So it would decide which backend to choose next. So there are multiple backend servers connected. Which one to choose next? So round robin, it distributes across sequentially. So 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. Weighted round robin, like let's say 2 requests goes to 1, then 1 request to second one, and 1 request to third one. So 2:1:1. This is the weight that you have configured. So it will do weighted round robin around that. Then another famous one is least connections one, which picks the servers with the least active connection, which means the server which is not busy is typically picked. Because with round robin, what would happen is, let's say one of the server is unlucky one and is getting a lot of long running requests, it might not be able to serve another request which is being forwarded to it. So that is where least connections one help us a lot. So these algorithms are in most cases configurable. Depending on the workload you are in, you should be definitely changing the algorithm at your convenience. Yes, for this kind of workload, I would not need this. Now, let's say if your system has all the API taking roughly equal amount of time, and there is no large deviation in the response time of APIs, you can have round robin. That works well. But if you know that your systems or your system does not really have almost unique or less deviated patterns. For example, one API is, or let's say 50% of API taking 1 second, while other 50% API taking 5 minutes. Like if you have this big of a variation, then least connections makes much sense. Like because the API servers that are responsible or the API servers that is free, the request will be forwarded to it. So API server or the unfortunate API servers that got a bunch of bulk requests or a bunch of big requests to handle might not be the best candidate to like serve your request. While the other API servers are starving to get like requests to serve. Right? So least connections is very well suited in that scenario. Right? Then comes IP hash. So this is a great technique. This is what defines stickiness. So these two algorithms are typically used when you want to introduce stickiness in your system. Let's say you would say that all the requests of a certain user should go to a certain server only. So that is where you would have like IP hash or header key value hash or something. Like all the requests from a certain geography or from a certain city should go to this particular server only. Right? If you'd want to configure something like this, so that you can have local caching and you can exploit those behaviors pretty well. Another thing is URL hashing. Let's say every request for /payments should go to this server. Every request for /profile should go to this server. Like if you want to build something like this. So this is typically handy when you are building something like an API gateway. So API gateway is what? Where I have a bunch of servers whose job is to handle that particular kind of request. Right. So let's say one service for payments, one service for profile, one service for communication, something. With URL hash, your configured key /payment should go here, /profile should go here, /email should go here. Right. So this is where URL hashing. So it basically hashes the URL or whatever it has got, and depending on that, it would send the request to one or the other. So URL hashing, URL prefix matching, IP hashing, all of those things you can configure your load balancers depending on which level is it operating on. Any questions? Okay.
Hey, hi,
Got
Rajendra. It's just one quick question.
got
So when we are implementing, say, URL hashing or the IP hashing, great that we induce stickiness, but wouldn't that kind of what is
No,
it?
but that is a
The amount
requirement.
of
No, basically that is a requirement.
oh, I see.
It's so basically the thing is ki algorithms are there. It is configurable. But if your requirement is that you need stickiness, right? That's when you would configure it. If you don't need stickiness, if you want everything to be stateless, then you would build it like that.
Got it. Thanks.
Right? So where would we use URL hash? A great example is if you are building your own API gateway. What is an API gateway? So let's say you have hundreds of microservices that are there in your service or product or whatever. And depending on like in the so API gateway is typically the front face of your ecosystem. Like every request would come to your API gateway. API gateway would see ki, array, my URL is /profile. It should be forwarded to profile service. My URL is /auth. It should basically be forwarded to authentication service. Like if you are building your own API gateway, you can leverage URL hashes for that. So more accurately is URL prefix pay hashes. So any URL that starts with a certain prefix should go to a certain set of servers. Like you can configure that. Chalo. Yeah, Anshuman?
Yeah, but, so I was wondering if you have an idea of how much latency is added to the system by adding a load balancer.
A typical latencies, you can assume 2 milliseconds for every hop.
Okay.
That's a really rough estimate. But typically 2 milliseconds is something that gets added. Yeah, Vikas?
So my question is like load balancer is also based on some service, right? So
Hmm.
which will in terms get all the APIs and it will examine okay what all prefix we are using for the URL has kind of
Hmm.
stuff. So what if there are multiple requests for the load balancers? How it is handled?
As in
Does it
multiple
crash
requests?
sometime? Like load balancer is also a service which may get millions of hits,
Hmm.
right, on their
Hmm.
API. So does it happen in like server like we have multiple load balancer or
So basically load balancer internally is not a single machine. It has
okay.
multiple machines.
So how they are interacting, like how they are tracking, like okay, this API request has been done, kind of.
API request is just normal TCP connection. We will come into the low level code of it on how to implement a load balancer so that you get a very detailed understanding of it. We will
Okay.
see in like 5 minutes.
Okay.
Okay, if you want to build your own load balancer, how would you actually do that?
Okay.
Right, we'll do that.
So, just Arpit, one question. So, like using Anycast is also kind of used as a solution to load balancing. So, would you consider that one too?
Anycast, it was I've asked this question to one of my seniors. Even he did not have a really solid answer, but I have never dived into it. If we can use Anycast for doing load balancing, I've
Cloud,
never seen it in production at
because
any
Cloudflare
place.
is completely on Anycast, as in their whole infrastructure runs on Anycast. The
Who's
CDN, Cloudflare.
Cloudflare तो CDN है ना, वहाँ पे Anycast might be there, but obviously not a normal product company would use Anycast for this, because I've only worked for those, so I've no idea, but I would definitely do a deep dive on that, how we can do load balancing using Anycast.
Okay.
So yeah, but if you have any resource around it, do share it. Would love to read about it, how to do it using Anycast.
Okay, no, I just read one blog. I'll just share that.
हाँ, जो भी है यार शेयर कर, पढ़ लेंगे लोग, मैं भी पढ़ लूंगा. ठीक है. What we'll do is we'll start diving into the low level code of load balancer. And one thing that you can read is read this paper called Maglev. Maglev is a load balancer. It's a software load balancer. This paper is a very simple read, but it would give you an understanding on how to actually build a load balancer. So इसमें पूरा end-to-end detail is covered. If you would want to build a load balancer, how would you do it? Okay. Now, what would we do is before we jump into the system design part of it, let's walk through if you want to implement your own load balancer, what all things would we need to do? I'll share my code base. So this is something that I wrote for the first cohort that I was fitting. It hardly took me like 1.5 hours to code this thing. It's a really simple one. Like it, and through this you'd see writing a load balancer is not hard. It's just that about handling those edge cases could be, but this would give you a very fair bit of understanding how, if you'd want to build your load balancer, how would you do it? So it's there in the repo on my GitHub handle /ARLB. If you go to ARLB, it's basically Arpit load balancer, something randomly my had to give. So ARLB is something that on which you'll find this code base. Right. So idea is very simple. With load balancer, what do we have? Load balancer is one process that accepts the TCP connections, right? And then it forwards it to one of the configured backend servers, right? Let's say behind the scene, we have 4 API servers on which we have to forward the request to. So one TCP connection from the client. So my load balancer would have to do what? Would have to create one TCP connection from the client which is there. So it has to manage that connection. And it would have to create another TCP connection from this load balancer to one of my API servers. So one connection from your client implies 2 connections for your load balancers. Correct? Given this thing, this is exactly what load balancers would be doing internally. So it would be waiting for something, or it would be waiting for getting a socket connection on its running port. It would have a list of backend servers that are there, right? Once it gets the TCP connection, or basically once it gets a socket connection, then it would be, depending on the strategy, let's say I'm going for round robin, depending on the strategy, it would be picking up, okay, this backend API server was done last. Now let's say it's round robin, I would have to pick this one. So for the second API server, I have the IP address, I have the port on which I have to connect to. Let's say my load balancer is running on port 80, my API server is running on port 8000. So my client would connect on port 80 to here. This internally would have one TCP connection with the client and would form one TCP connection with the backend server to whom the request needs to be forwarded to. Correct. This is exactly what our understanding of load balancer is, the fundamentals of load balancer. This is exactly what I was able to implement and actually load test. So it's a good habit that anything you build, you load test. If you load test, you would not to find out what the max limit is, but it just gives you like that confidence that it is indeed running, right? It is indeed doing the balancing of the load across system. Like, so build this thing on your own and see it to be like running on its own. So I've written this code in Golang. You can very easily write it in Java or this thing, C++. Python it won't work that efficiently because Python does not have the parallelism. So thoda problem ho jata hai. So, but yeah, you can still do it using async IO. So we will not go through the entire code, but you know the actual core logic of it. So this run function is something that is when my load balancer starts, it runs the run function. Right? So this run function is something that it does. What it does is it starts listening onto the port. So my load balancer is running on port 9090. Right. So my load balancer has just started on running on port 9090. And now what it has done is this, it has, so we'll come to it. So these are just set of commands that I can like do an interactive thing that I can type exit, so it would kill my load balancer. I would type add one more backend. I was just trying to, you know, I would try to add a new backend or new API servers on the fly to this system and see did actually started forwarding requests to those servers or not. So I was just trying that. So this is more of an interactive thing. Then I was on the fly changing the balancing strategy. So round robin balancing, static load balancing, hashed balancing, something. And by default, it's a hashed balancing, which I covered for. But okay, this is just for interactiveness. That's okay. But this is where the main logic is. So I have an infinite for loop running. Obviously, my load balancer, I would not want to, you know, I would not want it to be killed. It might crash, but it should not be like done for a certain request. So an infinite for loop which waits. I'm waiting for a new connection to come to me, right? My socket connection, which is open on port 9090, is waiting for a new connection to get accepted. Now, once I get a connection, right, what would I do is I would accept that connection and I would just print key what's the local address. It was just a print statement. Key what's the local address, what's the remote address or kya hua. But then what I did was I invoked a function called lb.proxy. lb.proxy is lb is my load balancer's class. And in that, I'm calling that function proxy, in which what I've done is I've taken a source connection, which was nothing but the connection which was given to me from my client. So this is the connection from my client to load balancer. I've created a normal object in which I'm putting in my source connection and a random request ID just to have that tracing ability key. This is a unique request ID which I generated. So every request ID is unique. I should be able to trace this request ID went or basically came from this client and is being forwarded to this particular backend server. Right. So this is what the requirement is. And this is where the magic happens. So let's see the proxy function. It's right here. So it gets the incoming request object. Now what it does is, depending on the strategy, it gets the next backend. So let's say my strategy is round robin. So my next backend would be index plus plus ka next element. So I might have just a array of, you know, all the backend servers, and I would just be doing a round robin on that. Right. So let's quickly check the strategy part of it. It's there in this code base. No, would be another one. Oh, code base, sorry, file strategy.go. So to give you how simple strategy is, like this is my balance strategy something interface in which I have init get next backend. So every strategy that I have would have a next backend function which would return me a reference to my backend server. Now, what's the backend server? Backend is nothing but wait, lb.co. A backend is nothing but a combination of host and port. That's it. That's what my backend server is. If this server joined the party, it's running on port 5000 on this IP address. So this is my backend which is configured, and is healthy is something that I would want to check if my server is healthy or not. If it is healthy, then only I'll forward it. So some metadata to store with the total number of requests that it has handled, so that I can implement least connection based something or lowest request first or something like that if I want to do it. So some statistics around key which API server handled how many requests, right? If I want to do that. So just added that, nothing fancy here. With initialization, I've just added, I've spin up 4 servers locally. Basically, local host pair, I've run the same service 4 times with 4 different ports, 8081, 8082, 8083, 8084, mimicking my 4 backend API servers. And whenever the request comes in, it would pick one or the other depending on whatever thing I have. Now, coming back to a strategy thing, let's check out how load balance. See, this is my RR implies round robin. So round robin balancing strategy is what? It has an index as a global or a local object for that particular strategy. And it is just doing index +1 modulus of len of s dot backend. So for all the backends that are available, I do a ++ and just do key, it is going in cycle, right? And I just return that particular backend. As simple as that. If I would want to do another strategy, let's say for static, in which I have like always request should go to this particular index only. That's what static is. Hash wala is something that you'll resonate more. This one, get next for a hash based balancing strategy. So given a request ID, so I'm hashing on request ID. So to make things random, so randomly it will be forwarded to any of the servers. So if I want to do that, I'm taking request ID, I'm doing a hash of it. This is giving me a slot, and I'm doing a binary search on it and finding out which slot does it fit. So basically, slot would give me what? Slot would give me. I've tried to implement consistent hashing over here, by the way. So typically, if you want to implement consistent hashing, we will go through that code as well. I've tried to implement consistent hashing over here. I have a hash string and to which my request should forward to, right? But you can pick it like slot modulus something, and you would forward it to that, right? So doing a normal hash based thing, right? So this is typically how you would implement a normal strategy. Now, once you have this thing, LB. So once you have a strategy, we were looking at into the proxy function. It's only this much of code, right? That's it. Itna sahi code hai. There is nothing fancy here. So you get the next backend to which request needs to be forwarded to. I just did a log printing key incoming request for this request ID is this. It goes to this backend server. And what I did is I set up a new TCP connection, right? So now that I have a backend server to whom I need to forward my request to, I'll set up a TCP connection on the backend.host and backend.port. And then once, if I have any error, then I'll just break the connection. Like I was just writing a toy load balancer, right? Once a connection is established, what I have to do is just copy. What do I need to copy? I need to copy everything from my, so the first argument is the destination. Second argument is the source. So everything from request.src connection. So src connection was from client to load balancer. So copy. So this will make a system call to copy whatever is there from my src connection, मतलब connection from my client to load balancer, and put it on to backend connection. So backend connection is from my load balancer to a backend server, right? And copy everything from my backend connection to my client connection, and these two will run in thread, right? And these are blocking IO system calls, which means my system call would wait until my either my TCP connection breaks or it gives me an EOF, basically end of file. Once it gets either of this, that's when my IO call would fail. Otherwise, it will be a blocking call. So unless and until my request is not sent from my client, I would not forward it to my server. So my first thread would be blocked there. Right? My second thread would be blocked until my backend server responds. And once it does, it would then forward, it would then do a copy to my client TCP connection. As simple as this. So these are blocking calls. But if I would not have run it, so by putting a go in front of it, I'm essentially creating a go routine, which is nothing but a lightweight thread. Right? By putting in a go, I'm just ensuring that both of the execution of both of this system call is triggered in parallel, which means if I would not have put go over here, it would have waited and waited and waited until my client sends all the thing to my server, and this is forwarded to other thing, and my client also sends EOF. Right? It would wait till then, and then once that is done, then my code would wait over here, and it would wait over here until my backend server responds and it's sent back to the client. Right? So to do this thing very efficiently, it's just that spin up in multiple threads because I want to handle things concurrently. Right? If I didn't run it on threads, things would have not been concurrent. So obviously my load balancer didn't make any sense. Correct. This is a very simple application of this is a very simple way to build a load balancer out of it. It's just this much. This is exactly the core logic of a load balancer. Like nothing fancy. You can write a load balancer within hour of your time. And a great way to understand that you are indeed doing that is by running a load test. So I've run Locust Pay. I've just configured one API which hits this part. On Locust, I've just configured one endpoint, which is port 9090 of my load balancer. 4 API servers or 4 servers running static site are there on port 8081, 8082, 8083, 8084. And I've just seen how many requests each one of them got by doing a console log. And obviously, the influx is something that I can control. Ki generate one request every second. So I could know ki one pay with round robin, first server pe gaya, then second, then third, then fourth, then again first, then second, then third, then fourth, and so on and so forth. Which proves that our load balancer is indeed working. Right? Any questions around this? There should be.
Yeah,
Otherwise, you
the
all-
one question. So
please.
Anshuman here, yeah.
Hmm.
So for each request, I should ensure that 133 is executed before 134, right? First, the client is transferred to backend, and then I get a response, and then I respond back to the client.
You
right?
don't have to ensure
But
it.
when I run
If-
them in two
since it's-
different Go routine,
So that would wait. So your Go routine would or your system call is anyway waiting. Like your IO.copy would actually fire that system call, and that system call is blocking. So you don't really have to worry about it because it's a system call which is waiting on that part. So it would wait until it gets something on it and receives an EOF. So it would wait on that part.
but I'm thinking, so they are running in parallel, right? In two Go routines. So what if 134 responds back before 133? So they are in two different threads, right? Basically, and they are like independent of each other. So
No, but
how do
that's
I
not how
ensure?
request. But your request response doesn't work that way, na? If you have a bi-directional TCP connection, that's a different way to load balance it.
Okay. Okay.
Right? Because that's, well, the code would be very similar, but you would just need to handle a few parts here and there. But through this code also, bidirectional TCP connection would work just fine. Like for example, what you're saying is, let's say without even request being sent from my client to my, let's say my backend server send something to the client. That could happen because it's there. Correct, because it's there. But whenever you start a server, the server is waiting for something to come there. That's when it would serve it. But if you have something like a WebSocket or a normal TCP chat based something that you have created, where if the connection exists, then anything could be broadcasted, it would be done there.
Okay. Okay.
Right, because both IO calls are independently blocked.
Yes. Yes. Okay.
Right. So
But here it
has
won't
input-
because until and unless the request comes to the server.
No, no,
Okay,
no, no,
here
no,
it
no, 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 not necessary. यहाँ पे भी you can handle that case. Like, because you don't really have to do anything, because the first IO call is blocking on my backend connection, or basically from my client to my backend server, it is being blocked. And my second IO call is also blocked. So both IO calls are in parallel blocked.
Okay. Okay.
Right.
Got it.
So
Got
even
it.
your
got
backend
it.
server can send it if you configure your backend server to be like that. Whenever the TCP connection is created, just start sending some random shit to
Correct.
it. It would do that.
Correct. Okay.
Try that out. Feel free to fork the repo and build it. It's a very simple. You can build. You can play around a lot of stuff around this. Right. But obviously, for the bidirectional TCP connection is something that I have not tested, but with theory that I know of, this code would work for that. You might just need to tweak a little bit, but as far as I can think of it, for the first run, you would not really have to tweak anything, and it would work just fine. That's what my first understanding. But what would definitely need to be done is, like, you have to, if you want to keep the connection persisted for a long time now, that's what you would have to explicitly handle. Okay, because now what would happen is, once you get an EOF, like, basically your server should never send an EOF, because once the server sends, so that's what typically happens with normal HTTP servers. So once it has sent all the data, it sends an EOF. Bhai, I have sent all the data. This is my end of file, and that's when the connection is broken, or basically that's when the system IO call is unblocked. Basically, it's killed. Right. So that is something. If you want to have it persistent for the communication between the two, then you would have to keep it open. That's the only thing that might have to change. Otherwise, it would work just fine.
What happens when the client aborts the connection?
The system IO call is aborted. Now, chalo, great question. Let's cover that. So now these two are running in two threads, right? Let's say my client press the control C or basically shut down the browser or something, and my connection broke. Now, once this connection broke, what would happen is this IO call would be terminated. Once this IO call is terminated, what is independently happened behind the scenes is your TCP connection is broke. So your socket connection, which was established, is broken. So fclose system call or an interrupt would be generated. That interrupt would be caught by this TCP connection. And once it tries to send it, so you get this error, upstream error when your server is not running. Similar kind of error you would get once your client aborts the connection, because then it would identify that my socket is not working, so I can't send anything, and this would result into an ERR. So your IO call would return an error code in that case. But we are not handling. So to handle it gracefully, you should have handled also. We should have handled all sorts of error code and check all of those cases. But it was just a dummy thing where I just wanted to test my load balancing thing. But obviously, you can do connection pooling, then error handling, retries, check some checks and whatnot. Okay, but typically, when any one of them, either server or client, aborts the connection or something, your IO calls would fail and your connection would say, "Chalo, I'm done." Your threads or your go routines would be terminated, because all it is doing is just running io.copy, and since io.copy returned, so your go routine is terminated, so you can spin up more go routines. Yeah, Costa?
So, are there any kind of these load balancers which directly hand off a request to a client, like to the server? So the requests don't go through the server through the load balancer per se. Like the internal load balancers can be like that, right? You just ask which endpoint to hit, they return that.
No. So the one so you are talking about the client directly making connection to the server
Yeah.
without going through the load balancer. That is a
Yep.
very different architecture. If you can again wait, we will be covering that part in 2 weeks from now. We'll be designing a system which requires that to be there.
Oh, okay.
Right? Uspe must discussion hoga apna ki how to even do that part. Okay. But yeah, that is something that is very heavily used anyway in the industry. Where instead of letting a request go through load balancer every time, because as someone asked, I really forgot to ask, how much of latency does it add when you add a load
Yeah.
balancer? It's typically 2 to 3 milliseconds. So if you are building a system that is that efficient that you would want to save that extra hop, and your server and your client can directly talk to your server, and here the client is typically another service of yours. Like once that connection needs to happen and you don't want to go through load balancer, these sort of architectures are very common. Right, so you don't always have to go through load balancer. So you can go through load balancer, get an IP to connect to, and then make a direct TCP connection to that server. This is something that I've personally worked on. So yeah, this is a plausible architecture. Yeah, Vishal?
Yeah, so here if we remove go routines, right, direct IO copy, then it will be a
Blocking call.
single
Your
a
code will
blocking
block.
where-
Your code will block there.
So one request at a time, right? Then
One request at a
ideally.
time. Yes. Actually, not really one request at a time because for one connection, so not really one request at a time, because what we have done is we have called this LB proxy in another Go routine. So you would also have to remove this Go as well.
Okay, yeah.
Right? If this is also removed, then
Yeah,
it will be
and
one
that-
request
that-
at a time. Now for every connection, by removing this to Go, what we would do is we would wait for the client to send request to backend server. That is EOF, and then server would send something back to the client. That would be streamlined.
Okay, yeah.
So you can't have bidirectional chat key, but directly without even requesting for something, my server responded something. That would not be possible.
Okay. So in that case, it will be only, I mean, serving one request. Once that request is served, then only next request be served.
Correct.
That
So
would be ideal.
so by removing these two and not upar ka go, if you are not changing, if you're not calling this proxy in another Go routine or in another thread, what you're essentially doing is you're streamlining. Ki pehle you would need to send everything from a client through load balancer to your server, and then from the server through load balancer to your client. This is what you are streamlining. But once we remove this Go as well, which means everything becomes blocking. So my load balancer can only handle one request at a time, because now this function call would not, or my code or my runtime would wait here until this is returned. This proxy is returned. This proxy returns only when this IO copy returns and this IO copy returns. So then my load balancer typically executes one request at a time. And within that, it would wait
Yeah,
for
so-
your client to send and then your server to send back.
So okay, so now as we have Go routines, right? So multiple requests could be handled at a time, right? So but it will also have a limitation, right?
Yes.
So to overcome that limitation, there will be multiple load balancers.
No.
I mean,
So first of all,
multiple
you
of
would
this program.
yeah, you would have multiple load balancers running on different servers. Each server can handle, let's say, your server would have a capping pool of that. It could run at max 50,000 Go routines at a time. You would be handling that. You would have a pool of Go routines, or you would have a cap of Go routines that you can spin up. Right? You
Yeah.
would not be going past that, because if you go past that, your server might crash. To avoid that, you would have a cap on all the things that you have, like maximum Go routines that you can run, or maximum resources that you can consume, and that's when you would have that cap. And similar to this, instead of having one load balancer ka process running, you would have multiple such servers running. Isme everyone would run the same piece of code.
So but then
Unko
essentially
balance kaun karega?
it will mean like load balancer will have it. Yeah, okay. Exactly.
I'll tell you how to do
So
that.
uska
वो बताता हूँ. Just wait for 5 minutes. We will answer that question. कि how to achieve that? Just 5 minutes. अच्छा 5 minutes.
Okay.
Actually 15 minutes क्योंकि बीच में break ले लेंगे. But हाँ, that is something that I already planned कि पता ना cover करना. ठीक है. चलो, one final question before we move to the next one. Yeah, Vishal. अच्छा पुराना था. अरे यार पोपट कर दिया तुमने. चलो. I hope you guys found this thing helpful. I was very amused when I implemented this. I wanted to cover something interesting in the first quote, and that's where I thought of, chalo, let's try to build our own and see if I could build it. I sat on Friday evening, Saturday I wanted to cover, and I was able to hack it. And I was like, "Arey, chalo, maza aa gaya." I'm like really happy after I did it. And chalo, ye to detail mein lenge because while implementing, obviously, I got a very detailed understanding of what happens, because I also fell into that same set of traps. Now, Ki, Arey, I did not create go routine for this. Arey, I did not create go routine of this. Acha, this is blocked here. Right. So all of those things actually happened with me. But I was unable to do that bidirectional thing because I was having an HTTP server running. So I never tested it. But theoretically, that should be possible. So if someone can surely experiment on that and let me know, that would be awesome. Yeah, Rahul.
So assume like more than one request is coming to the
Hmm.
load balance, more than 5 because the servers are 4.
Hmm.
So in that case, so is that load is handled by the server or the load balancer?
Acha, so the TCP connection,
Yeah.
the one, see, the TCP connection is anyway formed, right?
Uh-huh.
Now in the strategy code that we had, we have to handle that key if my existing TCP connection for this server is drained or not. Number one. Another case is your server typically queues up the TCP request coming onto them because those servers are not just handling one request at a time, because those servers are also multi-threaded.
Okay, yeah. Hmm.
Correct. So since those are also multi-threaded, then you don't really have to handle it. You will just forward the request. If that server is unable to handle it, the TCP connection will not be formed. Correct?
Yeah.
Thanks. Chalo. Let's take a quick break. About 5:15 ko milte, and then we will go into system design of load balancer. Ki what all components, although we have gone through the low level code of it, but we will still cover a few interesting caveats about how to load balance a load balancer. So that case needs to be covered, metrics, which protocol to use and something. And then the final thing which we would be covering would be distributed locks and its requirements. So आज भी शायद 6:30 तक जाएगा ही जाएगा. But it's fun anyways. ठीक है? So let's catch up at 5:15. Thanks, guys.
So meanwhile, everybody joins. Arpit, so how do you keep yourself updated with this design and stuff?
I just read a lot of engineering blogs. That's it. In case you don't know,
Okay.
I run a newsletter called the Great Engineering Newsletter. So in that one, I'll share the link in the after this thing. So it's on the site offtheday.in/newsletter. So if you visit offtheday.in, you will come to know how STM is. And obviously that is also built by me. I basically use it a lot to do my focused learning, and through that, whatever I read, I just schedule it in the newsletter. So in just one click, I add it to the next possible day. Any article that I like, any engineering blog that I like. So just visit offtheday.in, OFTHEDAY.in, and through that I manage my learnings and all. I add a lot of sources, and through that sources, I just cover the topic sequentially, and that's it. If any article I like, I just share it there. So most of the good stuff that I've already read, I've shared it through that newsletter. And yeah, so you can subscribe to it to get. I share one engineering article every day, every morning at 8:30 a.m. Monday to Sunday, and on Sunday I also send out a weekly summary of it, and it's free of cost, so you can just go ahead and subscribe to it. It's just about it's all about reading and reading. There is no shortcut to it. You just have to read, and more importantly, be hands-on with implementation. Like with load balancer, like most of the people have learned what load balancer is, but implementing it, gives you a very detailed understanding of things, and that is the differentiator. Chalo. Let's jump into system design part of it. Now, let's say if we were to do the system design of the load balancer. So we already went through the low level part of it, right? But with system design, what we'll be putting our focus on is like all the components that we need to consider when we are building a system like this. Like, so this would give us key, okay, for a system like this, acha, I forgot to implement this, or I should have added this component. So we would try to cover a broad spectrum of components that we would be needing if we were to design a load balancer. So the problem statement is simple. We have to implement a load balancer which accepts the request from the client and balances them across multiple backends. The key components is health checker, like one service that would ping all of the configured backends and would see if it is healthy or not. And if it is not healthy, you need to tell your load balancer ki, Arey, this server is not healthy. So don't forward the request to it, because if you are forwarding the request to an unhealthy server, it would never get fulfilled, right? So you would typically have to move that backend server out of your load balance ecosystem, or of your load balancer's ecosystem. I would not have to forward my request to this system. Then connection pooling, which is something that I did not implement. So you might have to have like few sets of pre-warmed TCP connections with all of your backend servers, because that is something which is constant, right? Once you have pre-warmed connections, so you would be saving the time into doing those three-way TCP handshakes, right? And using already freed up connection from the connection pool, right? That would help you gain even much better performance out of the load balancer. Stats engine, like which server got how many requests, or which server currently serving how many connections, through which you can implement least connection based algorithm. Then what's the average response time, right? If your load balancer is working on L7, what's the HTTP status code out of it? Correct. So that so all of those stats needs to be published somewhere so that you can take intelligent decisions out of it. One interesting caveat is the load balancer code that we just saw works on L7 because it's a software load balancer. It has HTTP requests. It gets the entire HTTP packet, but I implemented it like L4 load balancer because I did not decode the message that I was getting. Right. That's where in the previous weeks I told that I implemented an L7 load balancer, but implemented it like an L4 load balancer because it does not see the body, if you see, I just added io.copy from one connection and then io.copy on another connection, right? I could have done io.copy, or I could have read it, buffered it into my memory, then taken some action on top of it. For example, that's what Nginx does, right? You can have, when you're using Nginx as a load balancer, you can rewrite your HTTP request. You can add new headers to it. You can remove payload, alter payload, change something, change in the header, or do some manipulation on the request, right? So if you would want to implement that between those two IO copy, you might, so instead of doing IO copy from one connection to another connection, you would do a IO copy into a local buffer string, and then do that processing, and then rewrite that same thing into that other TCP connection, right? So that is where, you know, this part would come into the picture. Like you are changing something and building more like an Nginx. So if now you can component give what all logic would Nginx would have implemented to, like, you know, altering headers, adding new parts. So it has exposure to, so even we have exposure to all the data being sent, but we are not utilizing it. So that's where L7 load balancer implemented as an L4 load balancer, right? So that's that. We need backend discovery. So this is something like, you know, that interactive thing where I was having function add backend. So I can on the fly add backend, which would get updated in that in-memory list. Instead of doing this, there are some tools that does auto discovery. Like any server that has port 5000 open might be of my interest, right? I can have an auto discovery model, which internally can use Anycast protocol to tell you, hey, so then the server, when they boot up, they would do a broadcast, not an autocast rather, but a broadcast. Ki, hey, I'm alive. I have this IP address and I am running on this port. Any service who have auto discovery enabled can reach out to me on this IP address. Like as simple of this message as it can be, right? Once you have this thing, you can configure the system automatically. Like instead of you doing a manual entry key, array, this is the new backend which is registered, so I want to make an entry. You can automate this through this thing. Whenever server boots up, it does a broadcast. Implementation detail, you can Google. I have never implemented it myself, but I know how it was done. I've read it in Heroku's blog, most probably Heroku's blog or somewhere. So usme they have used auto discovery using multicast and broadcast. So they were telling us the difference between what to use when and why, something like that. Okay. Then header manipulation is something that we covered, how to do that. Proxy is something like your server is adding as a proxy, then algorithm plug that I want to change my algorithm from round robin to least connection based to hash based or something, right? Then you would need a metadata store to, you know, hold this information, like some metadata service which holds key, okay, I have these many. So right now what I was handling in the in-memory list, there can be a better way to put it, because now if I can't have list on now, my load balancer is not just one server. Like my load balancer could also be horizontally scalable, could be load balanced across, right? So it would not be just fixed set of machines. So obviously there needs to be a source of truth. Now that would be our metadata service that is giving us all of this information. Then you would need feature of request tracing, like having a unique request ID to see from where the request came in to where the request went and what was the response time and all of those part to have that part, right? So handling persistent connection is something that we discussed. How would we handle persistent connections? Adding it to connection pool, keeping the connections open. If the connection is interrupted, it's a job of load balancer to reconnect it, because your client does not know what happened. If the connection between a load balancer and backend server failed, it's a job of load balancer to reconnect it. If the connection between a client and your load balancer failed, it's the job of client to reconnect it, right? And obviously concurrency and locking would come into the picture, which is an important part which I did not handle. So see all of those things that needs to be considered while designing a load balancer. We will dive into a bit of it. Okay. Macro components is something that we have seen. Sorry. So our load balancers API server is this one. Sorry, this is the load balancers API server, the main where our code is executing. This is your metadata database that gets connected to load balancer to get, you know, what all backend servers are configured, what all system is there. So this is something like that. It might connect to this database to get that information. and has 3 backend servers connected, right? Now this load balancer internally could be multiple servers, as we already saw. Okay, this is where the interesting part comes in, right? LB is definitely not a one server. So how do we scale it? So typically load balancers are scaled using domain, using DNS, right? So what you can do is in DNS or in Route 53 specific to AWS or any DNS configuration for a route, you can configure not just one IP address, but multiple IP addresses, right? So let's say I have 4 instances of my load balancer server. So these are huge machines. Instead of having one machine, let's say I have 4 machines of my load balancer. So let's say odd.google.com, or let me give it a better name. Let's say this is LB. Let's say this is load balancer dot google.com. Let's say this is Google's internal load balancer or public load balancer, whatever it is. Right. So in its DNS entry, it would have configured 4 IP addresses: 10.0.0.1, 10.0.0.27, 10.0.0.37, 10.0.41 for 411. Right. So these 4. So now what would happen is the weighted round robin or whatever strategy you would want to apply would be applied where? On the DNS side of things. So DNS may, since these 4 IP addresses are configured, it would see, I got a request for lb.google.com. Now internally, I can forward it to one of these things. So let me pick one at random and would forward it to it. So you can do weighted round. So you can do weighted. You can do a weighted routing here. So with each entry, you can configure the weights to it. What's the weight of this particular entry? So let's say I can say that 20% of requests should go here, 30% should go here, 40% and 10%. So I can have this sort of weights configured here. Right. So this is how we can load balancer. Right. So when I'm getting this 4 requests, my user is going to the DNS, right? My client's request is going to what? lb.google.com. It is then reaching out to what? From this load balancers, or rather google.com is something. Google might confuse you. Let's say this is your own private thing. So example.in or something, example.internal. So these are our private load balancer, right? So let's say we are AWS and we are building our load balancer service. So it would have multiple servers now. So those 4 or 5 or 100 servers, how many servers would have been there? So the load balancing logic has been offloaded to a minimal load balancing logic on DNS side. So these 4 entries have been configured on DNS. So whenever, so the URL which is communicated to the client to whom the connection needs to be happened on is this one. Now, whenever this request happens, it goes to Route 53 or your DNS server. Maybe you're using a core DNS or whatever you're using. Pick that. In that thing, you'll be configuring it. And then it would internally, depending on the logic, let's say there are 100 entries, you have 100 humongous load balancing servers running. It would pick one and it would then forward the request to that particular thing. Right. So here we have offloaded our load balancing to DNS. Right. So DNS is where we are doing. So now these load balancers are humongous machines, might handle millions of connections at once. Right. So you don't really need many entries here. Right. So that is why you would see every time you are creating a load balancer, it gives you one load balancing endpoint. Or if you have configured your own GoDaddy or Namecheap or something, and you have changed your namespace servers, it does not give you one namespace servers, it gives you 4 entries for your namespace servers. Like similar to that, because it is trying to load balance across those 4. At least one of them would have it. Sorry, all of them would have it, and internally it could do that balance. And this is exactly how we would be balancing, or we would be load balancing our load balancers by offloading it to core DNS servers. And here we would not have like thousands of entries. We would have for each load balancer, let's say 100 servers which are capable of handling this load. So those 100 entries would be there. Let's say one new server is added to it. The new server is added, or new server is spun up. Let's say you want to scale this up. So you would add one Magnum server, let's say LB5, and you would add its IP address here. Right, and that's what would happen. And this one server is capable of, let's say, handling 1 million or even 2 million TCP connections, right? So which means this sort of events would not be that frequent as compared to other scaling up events, right? So this is how you can scale up your load balances. Any questions over here? Because this is a critical thing.
Every load balance, the earlier problem of every load balancer then has to keep maintaining a persistent connection every backend server that we already discussed with when using the reader replica example. That again gets introduced here, right? Because as you keep adding more load balancers, each of
Correct.
them.
If you are having persistent connection, then that becomes a problem. That is why a heavily persistent TCP connected systems are very expensive to manage.
Right.
Yeah, but in this case, so if we are having 100 backend servers, right, distributed among these 5, right? So are common across these 5 or 20-20 each sort of a thing? Because if a particular load balancer goes down, then that 20 batch would go down, right?
So that depends on the strategy. Typically, it's like basically randomly assigned. But if you are aware, if you are building your own load balancer, you can tune it to yourself, like how you would want to have that part key. You can have a hash based approach where you say for this service, let's say on this load balancer, you might have like 4 or 5 services, for example, right? Okay, you might have like 4 or 5 different kind of services. So let's say each service goes to just one load balancer. You might have that. So, but when that happens, if that load balancer servers goes down, it takes that entire service with it. But if that is something that you are living for, then go for that. So that depends on kind of tuning you would want to do, but the implementation approach would be something very similar.
Okay, and by any chance, if one of the requests from DNS routing that came into one of the load balancer, that let's say 1, right, 0.1, and somehow after reaching there and then hopping to backend and the connection broke, right? So would it by any chance be possible to reroute the request to 2.7?
No. The client,
No, right? It will be 500.
because your DNS server does not know who the client is. Correct?
So again, it will be a 500 error.
That's the problem. Yes, because client might be in an internal network, might be wherever, because that's why server cannot reach out to client. That's why you need TCP persistent. There is a TCP connections are persisted unless the transaction ends. Because otherwise there is no way for anyone to figure out who the client was.
So there would be a TCP persistent connection between the DNS. So
from client to DNS, so typically from DNS server, you will get the IP address to connect to, right? That's what the DNS handshake happens, right? In which you get the IP address to connect to. That's it. So then it would directly connect to that particular IP address, which means what it is getting is IP address of one of the 4 load balancers that we have. So then client is directly connecting to that.
Okay.
And that's what.
Go on. And then I mean, if we open the network tab and then try to see what is happening, so we won't see where the DNS thing is coming, right? We directly see that.
Using dig command, you would get all possible IP addresses to which it would be resolved. Right? Through that, you would be able to find what all IP addresses are configured for this. So even for the AWS load balancer, if you do dig, you would find 4 or 5 IP addresses.
Okay. Even TraceRT would do similar stuff, right?
Yeah, could be. Yes. I'm not really aware of it, but yeah, they would be doing something similar.
Okay.
Sure. Any other question before we move forward? 1, 2, 3, 4, 5. No, sure. I hope you guys understood it well. If not, feel free to reach out. Okay. Now, this is something that we covered. What each LB server does, it receives an incoming request. It finds a suitable backend server to connect to using the algorithm. It connects to the backend server, forwards the request to it, and waits for the response, and then forwards the response back to the client. Right. So this is basically this is a mota overall gist of it. But again, the implementation depends on the kind of use case. You might have a long running persistent TCP connection for a bidirectional communication like gRPC or WebSocket or something. Depending on that, you would alter the strategy. Nginx and other load balancers do much more than this, but mostly around manipulation and routing and edge case handling, like retries and all. Right. Those things is something those like these sophisticated systems are built for. Like so there have been thousands of contributors to such projects. Few things that obviously we have already discussed and shared. Few things about it. What makes a socket unique? Max sockets per server and why? And load balancing algorithms on almost, and actually for the first couple of things, the resources are already there on the Discord channel, where we were discussing how to have 1 million concurrent connections on an EC2 server, and one video by Joybo Hussain Nasser, which explained what makes a socket unique. So those two resources are already there, and obviously go through the load balancing algorithms. We already saw how to implement 3 of them, but we can pick others and go. Okay. Now, other macro components that we would need: Heartbeat server. So the job of Heartbeat service would be, it would be a separate service. So it would not be part of your API, your load balancer API servers that are doing that part. Might be a separate service that pings all the registered backend servers once every minute or something on the configured health check port and sees if it is alive or not. Right. So typically, whenever you do configure any load balancer, it asks you for a health check endpoint, right? And this is where you might have a separate service whose job is to repeatedly ping all the configured backend servers. If it is alive, well and good. If it is not, it would immediately throw it out of the registry. So that's the main job of Heartbeat server. So it runs independently of your load balancers. It would run as a separate component, would talk to your registry database. From that, it would get the list of backends. It would ping, got response, all good. Once the response is there, it would say, and it would update this thing, healthy. Once it found once it did not get response from one of the servers, it would mark it as unhealthy. Once it is marked as unhealthy, your load balancer would not send request to, or basically forward request to that particular server. Right? That's where the hardware system comes into the picture. And then a trigger system. This is an interesting one. So what would happen when it has found an instance to be not working? Like it is an unhealthy instance. So these are all events. So you might want to do something around it, not as a load balancer thing, but maybe as an external consumer, you might want to listen to those events and see if something is happening or not. Right. So upon an event, issue and trigger. So the PubSub that we discussed, right? So this is something that you would have some events happening. You might want to throw all of those events into a Kinesis or Kafka and do something about it. Maybe within your load balancer service or across your ecosystem. Maybe what you would want to do is send it out to your analytics server saying like one metric that AWS throws is the number of hosts behind your load balancer. Like every minute it throws that metric, what's the number of hosts behind your servers. So if you'd want to throw such metrics out, or if you'd want to see all the events that happened on a load balancer, you might want to send this data through a Kinesis or Kafka or SQS or any broker that you would want to pick. This event happened. Let's say my Heartbeat service pinged this backend server. It did not respond, marked it as unhealthy. So these events can be sent through the system. Now, who will be consumer of this event? Either your load balancer service, who might take some action. Like let's say updating in the database, updating in the analytics engine or whatever, right? Or maybe maybe pinging the core API server of load balancer to not forward the request to, if that is how it is implemented. So implementation is wide open. However you would want to implement, you can implement. Like, but pick one over other. Do it event driven, do it ping driven, or make a database call every time. So there are multiple ways of doing it. You can pick anywhere, but a trigger system is essential for this. Right? Wherever we can send critical events, and critical event does not really mean that something bad has happened, but even something good. Let's say one new server is added to it. Like this trigger can be sent to your billing system, where let's say your billing says that depending on the that your load balancer is charged, depending on the number of hosts which are or number of healthy hosts which are connected to it. Let's say that's a billing criteria. If you want to have that, a trigger system is ideal to have this communication or your load balancer service ka communication to happen with the billing system, right? So you'd be streaming out events, and through that, your billing system can be kept in check. Just an example, right? So there could be thousands of use cases for this. You can pick and choose whatever and wherever you would want to implement this. Then comes stats engine. So all of the stats from the load balancers are exported. Your load balancer continuously emits the stats. What's the current number of TCP connection that it is handling, incoming TCP connections, 4xx, 5xx, 3xx, all of those counts. Maybe request getting from a certain IP around that. Because through that you would know ki, Arey, I'm getting a lot of requests from this region. I might want to do something about it. A lot of things can be done. So you need a stats engine to do this, which exports all the metrics. So you might use a Prometheus for this, right? If you have not heard of Prometheus, we will cover it in a few of the use cases in the future. Just do a Google about it. It's a very efficient time series database with visualization and a lot of other features. But the best part of it is not push based but pull based. So what happens is a Prometheus server, what it does is, instead of you pushing your data to Prometheus server ki go ahead and store the data, Prometheus server will go ahead and pull the data from it. So your server would expose, your server typically exposes an HTTP endpoint. On that endpoint, in a certain format, the metrics are exported. Prometheus, once every configured frequency, let's say once every 5 seconds, it would make an HTTP call to the backend server on that very endpoint. Let's say /metrics on port 9000. Your Prometheus server would go to all the servers on this port. It would make a call and get this metrics and save it. So here what happens is Prometheus server is not bombarded with the metrics. So it would pull at its pace. Let's say Prometheus server is overwhelmed by the number of servers configured. It might just miss out on a couple of points here or there. Right? But that's the advantage of it. So here the stats are exported but not sent to Prometheus. Rather, Prometheus pulls the data from. This is what the difference of a pull-based versus push-based metrics is. It stores data in InfluxDB. It is built on top of InfluxDB and stuff. So Prometheus is a very, very hefty tool. If you have not used it, go ahead and use it. And you can do visualization on top of Grafana. So never heard of Grafana? Grafana. Google about it, get hands-on and see how great of visualizations you can build on top of it. So this is how, if I were to design a stats engine, I would do that. So that every server, like all the metrics from server, like CPU stats, memory, network, disk, all of the stats are exported from the API. So this LB1, LB2, LB3 are the 3 API servers of my load balance, of my single load balancer. Like, so for that encompassed or the enclosed load balancer, I might have multiple servers, right? So for this, I need stats. Array, this server ka CPU utilization went very high, so I not sending out requests to them, or maybe replacing the server or do something around that, right? So those, for that, if I'm measuring it, I can take actions on top of it. So which is where stats become very critical. So these stats are not just for the others to consume it, but even for your own system to take care of it. My CPU is going very high, my memory is going very high, I need to do something about it. Right? What else to explore? This is the code base which I showed you. /ARLB on my GitHub. You can check that out. Do read about blocking network system calls and how to handle them. Like just try out removing or making things non-threaded and see what happens. Implement that was a great discussion that we had. Implement a bi-directional communication. So instead of server client response, your once the TCP connection is implemented, both are like constantly bombarding messages to each other. So in that case, what happens? Something like that. So this covers load balancer. Any questions around this before we move to remote and distributed logs?
So Arpit, around the metrics that you have mentioned, what are those metrics /metrics that Prometheus pulls? Is that log?
So you can publish any metric to it, but it has to be in a certain format. So you can have a node exporter is something which exports CPU, memory, and other metrics from the machine on that endpoint. Okay. Other thing could be number of request that that particular server is handled till date, or that server is handling at that point. Right? All of those stats, like how much of request each of your load balancer is handling. So that then you can aggregate and give out ki this is the load balancer and these are its stats.
And like actually another question. So this is more around, circumventing the whole load balancer session that you've given. So ideally, when you scale a system, right? For example, this Google Pay, Phone Pay kind of a system, when they started with some similar like limited number of users, and then users kind of scaled up over time. How do you decide on like when this system needs to be scaled? Is there a certain heuristics that goes behind it? Because like what it looks like, again, I could be wrong over here, that you have a DNS server, right? Which is where people are, polling to or, requesting it to. Now this DNS is actually forwarding all this request to load balancers and then so on, right? So how do you, like, what are the heuristics that goes in to when to add more servers, when to add more
So
load
this
balancers?
typically goes with CPU and memory stats of those instances. Right, and basically that's what decides when should you scale up or not. So if your average CPU utilization of all the servers behind a load balancer is about 50%, there is no need to add more server. If it's a CPU intensive workload, right? So those are when basically those are the metrics that you should be tracking. The average CPU utilization, average memory consumption. Most scaling happens on that. If you are building a system that consumes message from a broker, you would be scaling system on the basis of number of messages available in the broker, right? Because you would want to consume messages as fast as possible, right? So depending on that, you would be defining your scaling policies.
Okay, so what it indicates is like you would start monitoring from day one itself,
Correct.
right? Once
Correct.
the system.
Without monitoring, you can't. You would never be able to take a good decision.
Okay.
And
And is
basically,
there an auto scaling setup? Usually it does
with
for all these
AWS,
cases?
AWS by default gives you auto scaling. So if you are cloud native, every single cloud solution has an auto scaling policy setup. So you can configure, let's say, so you can configure rules like when my average CPU utilization goes above 40%, add n servers. Now you can configure n to 5 servers, like depending on your workload. If your average CPU utilization goes below 30% for 5 minutes straight, remove 3 servers, like something like that. You can configure rules like this.
So different policies for this.
Different policies, yeah. So these are in AWS ecosystem, it is called auto scaling policies.
And sorry, just like before I conclude, I just need to validate one particular fact. Like all of this request goes to DNS, right? So DNS is the one system which takes all of the requests that are coming in. Right? Okay, okay.
So obviously it's like basically we offloading everything to DNS ki just sambhale, we can't do very much.
Okay, okay, good. Thank you.
Yeah, Vishal.
Yeah, so our load balancers would be very heavy machines, right? I mean, it will be a vertical, fall into vertical.
Vertically scaled machine. Yep.
So, have you ever seen a particular load balancer going down? I mean,
a lot of times. So again, not to quote it, but at Amazon, we had our typical load balancer sort of setup where a couple of machines were acting like load balancers to us. And to implement the thing where from the load balancer, we used to get the IP of the server to connect to. So the request never went through the load balancer, but load balancer gave us the IP to connect to that particular. So those
similar to DNS.
Yeah, correct. So basically similar to DNS. So those servers typically used to go down.
Okay. Yeah.
So that is where you would have to do error handling. Here, my server is going down. It has to follow this SLA, request timeouts and all. So all of those edge cases, error handling, that needs to be very sophisticated.
Okay.
Yeah. Yeah, Ankur?
Yes, sir. Arpit. So, Arpit, just to get the metrics out of the server, do we need to install some Prometheus client on every server?
Correct. Yes. On every server, you need to have a node exporter process running. This is something that comes as an offering from Prometheus, all the open source plugins which are there. usme there is one plugin called as Node Exporter. So I chose Prometheus here because I wanted to give you all guys a glimpse about, you know, an interesting approach of actually fetching metrics. Like almost whenever we think about things, we think about we'll make an HTTP connection and then that would store the data. I wanted to bring out this point. We basically just introduced Prometheus into the scheme of things. This is something which is interesting, which pulls the data from the system. Like, so you guys would be aware of yet another system or yet another kind of paradigm which you can use to build systems. That's it. But to answer your question in this, there is something called as Node Exporter, which you can use to export them.
I have just one more question. Like this Grafana, if I need to show something on Grafana, so it will use Prometheus.
Yes,
Prometheus only
Grafana has support of Prometheus as a data source.
Okay, so internally it will use Prometheus.
No, not internally. Grafana, but you have to configure your data sources. So you can give it Elasticsearch, MySQL, InfluxDB, Prometheus, Enjoyable, Timescale DB. You can configure any data source and then write queries to, to draw those charts.
Okay. Thank you.
Let's move to the next part. Aaj ka aakhri wala topic, where we'll be talking about remote locks. So remote locks is the most essential thing which drives. So remember in the first slide where I wrote about coordination and communication, right? So two systems that run in parallel can coordinate with locks, right? But since it is a distributed system, you can't use mutex, right? Because it's not a single process, right? So mutexes are not possible. So what needs to be there? There needs to be, like, if you are using mutex or mutex in with respect to our operating systems lies within your system or within your process context, and that's where it helps you coordinate between threads, correct? But here there are multiple machines, so you need one central source of truth which does that lock, which acts as a lock manager, right? So we would typically want to have remote locks or distributed locks in the system that would help us coordinate between multiple machines of it. Okay. So these are typically centralized systems. Like you have a lock manager, you have P1, P2, P3. These are three separate processes, as in machines. So three separate machines trying to coordinate between each other through a central locking system, which is remotely set up, right? If this was a single machine, you could say that P1, P2, P3 are three threads which are using a common mutex which protects your critical sections, right? In terms of when you scale it up into a distributed system, these are three systems or three separate servers who would want to coordinate using a central lock manager, right? Now, what it does is it would help you take locks on certain entities of a system, right? And all process, servers, services, everything would coordinate using this lock manager. Now, this is a paradigm. This is how you can implement it. But implementation on what to lock, where to lock, this is all up to the business logic on how you would want to do it. Okay. Can someone give me a great example? Can someone give an example of a remote locking system where you would have an architecture like this? Where would you need a central locking system? Anshuman, you have your hand raised.
BookMyShow, but
be a little more detailed around it.
when you are booking your tickets, then like you have to apply locks, like there will be many servers behind it, and then like let's say I go on P1, and then seats, so P2 must also be logged. Like any other visitor might not be able to see those seats as well.
Okay. Another any other example, guys?
And we can do that at database level, right?
But still it's a central lock on database. So see, again, this is a paradigm, right? implementation could vary. You can use Redis, you can lock it on database using explicit locking. You can use SQL locking for rows. But all of those, if you see, they fall under this centralized remote locks. Correct. So basically, that's what I said. Implementation could vary, but the paradigm would remain the same. So this is more about our thinking to be streamlined. We need something like this. Implementation could be like, I can use Redis, I can use a random server which access my lock manager, I can use a SQL database which is acting as my lock manager. Any other example?
It would be really slow, but some collaborative documents like Google Docs or something like that, where you're multiple writers on the same document.
That does not effectively use locking. It uses three-way merges. Locking is an overkill for it because it would slow things down. So typically when you have locks in the system, you are essentially streamlining things, right? So once the lock is released, then only something would start. But with collaborative documents, you would not want to have that because like assume that someone else is writing and I'm just blocking, I can't do much there. That's a locking. Collaborative editors work on fuzzy merges and stuff, and it has locks, but a very different kind of locks. So you can search about differential synchronization to understand more details about it. I might not be able to cover that. Yes, Sarthak?
Yeah, so one example which I have seen personally being used at Postman. So there we had this monitoring system where we would, schedule runs of specific collections on Postman that is being run on cloud. So in that case, we can have an orchestrator, and then those orchestrator can have different workers which run those collections. But now what problem arises is these orchestrators themselves are distributed and there are multiple orchestrators, hundreds of orchestrators. So in that case, an orchestrator would want to lock before acquiring a particular job to be run. Because if different orchestrators acquire same job, then basically it is waste of resource.
Correct.
So
nice.
So in a similar kind of system where we have multiple orchestrators, multiple workers, we can use.
Great example, Sarthak. Thanks for sharing. Great example indeed. So this is a classical example where, the things are idempotent. As in, if the same test job gets executed twice, it would not really matter to the user, but it's waste of resources on your front. So you would want to lock it. Let's say one of the executor is saying ki, I would want to run this job, right? So that executor takes a lock on that, right? And that lock wala thing, once that lock is taken, other executors can't take that lock. This way we are ensuring that one job is executed just once, right? And not mental. Another great example of this could be a distributed cron. Right? Just imagine CloudWatch gives you alarms, like having a distributed cron. Like let's say you would want to schedule something to happen at a certain time, but not on a certain server, but it needs to be distributed because there might be millions of events that you are configuring. So you would have something like a distributed cron. Let's say it has 3 or 4 different servers and all of them runs on that same cron schedule. And on that one time, let's say 3:55 p.m. I want to send every one of you an email that says कि class ka schedule is this thing and this is the link on which you would have to join. Now, what if 2 jobs pick that, or 2 jobs executed same, 2 jobs executing at the same cron time? Like my cron job is configured at 3:55. It is configured on both the machines. Now, what would happen is you would be getting email twice. You would be getting that message twice. I would not want to have that bad user experience, right? So to build distributed cron, locking is an integral part of it. You would want to, once that particular job is picked up, I don't want that job to be picked up by any other, right? This is where this thing is. What is now my question? What is that one property that this lock manager needs to have for it to implement, or for it to implement locking? What is that one property without which you cannot implement a lock manager?
Q.
Why?
Acidity.
Acidity.
Acid.
So out of that acid, only one is essential. I think one is the most essential. Without that,
Atomicity.
atomicity, because through others you would still, like with isolation you would get concurrency, with durability you would get you would get basically fault tolerance and all. But with atomicity you would ensure that if your things are atomic, right, which means your transaction is atomic, which means no other thing which is already running in parallel can interfere with it, right? It's one or none. That's when you would have a true lock manager, because when someone is acquiring a lock, others should not be able to do anything about it, right? So that atomicity is very important here. Acid, if it's acid compliant, that's the best part. But atomicity is a very, because most of the systems are anyway concurrent, or they execute in parallel, and also those are anyway sorted. What's not so famous, or what not so common, is atomic operations or some sort of atomicity in the system. So now why I was putting this much of stress over here? Now, instead of looking at what you can use as a lock to restrict your options to, like, maybe I can only use Redis to do locking, or I can only use DynamoDB to locking, right? Think about it. You can implement locks on any system that supports atomicity, right? In terms of atomic transactions, in terms of singular expressions or single statements or counters or atomic anything that gives you atomicity, you can leverage that to implement locks. We will take in future weeks, we will go into more sorts of locking and see really great ways to implement it. In the last cohort, since the CoWIN portal was new, we went into how would we implement CoWIN portal on DynamoDB, right? Just think about it, because you need locking, and if you want to do it, how can you do that, right? We will be discussing optimistic and pessimistic locking, but the key idea is, wherever the core feature that you need to make locking possible is atomicity. Any place where you see atomicity, you have to leverage that to have locking. If you don't, if the system, or if your code is not atomic, right, if your implementation is not atomic, so correct, even if the system does not support atomicity, you can still have a application level atomicity using compare and swap. If you don't know about it, add it to your notes, Google about it, like compare and swap. So anything, the GROM requirement for you to have this thing is your process of acquiring a lock has to be an atomic operation. If it is an atomic operation, you can implement any sort of locking on top of that, right? That is the core of it. So typically lock are implemented in real world, are implemented on top of Redis because in memory and fast. But since the base requirement of it is atomicity, you can even implement locks on DynamoDB, because every single DynamoDB operation is atomic. You can implement locks on SQL storages, because SQL gives you acidity. Acidity ka A is atomicity, right? So anything that gives you atomicity, you can build locks around it. So although a lot of literature on internet would say, Redis is the lock, no. You can build locks on anything, because CoWIN portal uses DynamoDB's atomic operation to have locking, or for you to reserve books when, let's say, millions of users are trying to book that one slot on CoWIN portal, right? It has to handle that much of concurrency and locking and all. How would it doing it, right? So it uses DynamoDB's atomic operations to achieve that. So that's the core part of it, and that's what you should be, that you should be living by. Key, wherever you have atomic operations, or you can implement atomicity, that's how you can get lock stuff. A great example, as basically very well put by Sarthak, is to have central locking system is about ensuring that one thing is not picked by multiple. A great part of it is like, how about building SQS consumers? Like, let's say you have a message broker and you have to ensure that one message is consumed by just one of the consumers, right? You don't want to have that message to be consumed by multiple consumers, because one message processed twice. Let's say this message is about sending an email to a certain group. Now if one message is consumed by multiple folks or multiple jobs, the email would be sent twice, right? Waste and bad user experience and whatnot. So SQS guarantees exactly once delivery. Actually it guarantees at least one, but in most cases it is exactly once delivery. So how if you would want to implement it, how would you do it? Note, this is not an exact implementation. We take this example to understand the need and the usage of remote locks. This is a disclaimer, right? But this is for us to understand why this, how are we leveraging this? Because this is a very must example to understand the need of locking, right? So what do we have? We have a broker which holds a lot of messages. Like, so messages are coming in, and there are consumers which are processing the messages out, and messages are held in this queue that we have. Now, what do? We have multiple consumers. Instead of having one consumer, obviously we have multiple consumers. So a lot of producers are producing messages into this, but a lot of consumers are consuming message out of it. Let's say C1, C2, C3 are the three consumers which are consuming messages out of it. Now, what do we want? We want exactly once delivery of the messages. But what we assume is that, let's say SQS does not guarantee it. So broker does not guarantee this. So we have to implement the logic on the application side. In reality, SQS gives that. Okay. But what do? We take this hypothetical situation where we see that application is not, or SQS is not giving us this. So we have to ensure exactly once delivery of the messages that we pull out of it. So anytime my consumer pulls the message from the broker, it would get the first message which is there. But what we have to ensure that one message that is there, it goes to just one consumer. Right? This is what we have to implement. So our pseudocode of consumers would be like this, where my consumer, when it runs, it acquires a lock, then reads the message. So when it reads the message, it reads just one message out of it, and then it releases the lock, right? This is nothing but the critical section. This read message is nothing but the critical section. And then once the message is read, it then processes the message, because now this could this is something that I don't want to be protected, like do the processing on it. So acquire lock, read the message, and release the lock. Now, what do we need? We need something remote that would act as a lock manager, because the consumers are running on 3 separate machines. Right? So we need a central support. We need a central source where I can have my lock manager as implemented. So it should support isolation. It should support atomic operation. TTL is very essential. This is a very interesting thing, right? So TTL is required. Otherwise, deadlocks would be there, right? So if we have TTLs, this would help us, our system to not choke up in a deadlock. Rather, if it finds deadlock, eventually my deadlock would be resolved, because once the TTL is there, after a certain time, if a message is consumed by, or if somebody is waiting on something, that relation would be like automatically be deleted after the TTL happens. Let's say my TTL is 5 minutes. So worst case would be 5 minutes of my system would be in deadlock, but after that things would be resolved. So support for TTL is critical. Redis fortunately supports all three, right? So that's why the most popular implementation of a central locking system is using Redis, and obviously it being in memory gives you that lightning fast speed, right? So what do? Is we register ownership on a key in Redis. Let's say I want to acquire lock on a certain message, right? Let's say message ID 123. So I would say in Redis, I would hold that key is 123, and the value would be I'm consumer C1. So I'll put 123 C1, right? So now this is how my would look like. So I have taken a lock on message, but instead of taking lock on the message, what I would want to actually streamline is, because my function is what? Read message would give me the first message which is there in the queue, right? So instead of taking lock on the message, if I take lock on the queue, okay, who can read message from the queue is something which is streamlined. So so what I have to actually streamline is read message call. So I would take the Q7. Let's say Q7 is the queue ID, right? On which my consumer C1, C2, C3 are listening. So I would have Q7 pay lock is with consumer 1, which means consumer 2 and consumer 3 would wait until in the Redis Q7 key entry is deleted. So there is no one holding a lock on Q7. So consumers would wait to get the lock on Q7, right? Unless and until and they would understand they would want to acquire the lock on Q7. For that to happen, the Q7 entry should be khali. Instead of it being vacant, we typically delete the key. So the key of Q7 should not even exist. Then only I can say that, okay, my Q7 is up for the grabs. Consumer Q2, consumer C2 and C3 would have that infinite loop running, go ahead and poll, go ahead and poll. They would poll it, they would not find any entry, they would try to get that entry done. So the set operation of Redis is atomic. So one of them would succeed, whoever succeeds. So people would typically set and get. Once it sets, set is okay. So once set happened, it would get. Once it gets, and then it would check if it is my consumer ID or not. If it is the same consumer ID, then it would go ahead and process the message and all. Right. Typically, this is how you can implement locks on a system like SQS Consumer or anywhere you would want to have central system. Questions around this?
I have one question. So, so I also have to ensure that. So let's say now it is null, right? The consumer is null for that queue. So now there are two other services, so they can be concurrently trying to get the lock. So on that also, I need a lock, right?
Yes.
It should be synchronous, right?
Synchronous.
Okay.
So basically, the same set of code would be running, right? Where the consumer is just trying to acquire a lock on that queue ID, right? They would be doing that part. They would be talking to Redis continuously, would doing a get and set. So they would be getting and checking if the lock is available or not. If it is available, I'll acquire it. Right? And this has to be an atomic operation. So that's why we are using atomicity of Redis to achieve that. Yeah, Rahul?
Could you go back to the previous one, which you mentioned about the log, the critical session?
Just this one.
So this is written at the code level, right? So like how it's central locking. So
yes,
if the two
this is on the consumer side of things.
Okay, so if the message is sent to two different consumers, still it will be a duplicate one, right?
Yeah, but that would never happen because only one queue would only one consumer would acquire a lock, would read a message. Once the message is read, it would obviously delete the message of the broker would be deleting the message, and then it would do the release lock for other processes to acquire it.
Okay, so it's adding a queue at the broker level, not at the code level.
Correct. It is locking at the queue level. So my consumers are locking the queue because read message is doing what? Read message is simply picking up the first message of the queue and just using it. Right. So that is where once the message is read, my broker is automatically deleting the message. Right. So once the message is read, it has deleted the message. That's when my consumer would acquire the lock, read the message, which means message is also deleted, and then it will be releasing the lock, which means done and dusted. Right. So now other consumer is free to read is basically free to invoke read message, which would now pull the first message from the queue, which would now be the next message in the queue. Sure.
So consumers are constantly polling that code, like looping on
correct.
code.
So that's a typical implementation of acquire lock function. So acquire lock function is typically an infinite loop which continuously bugs the Redis server or your central locking system to see if the lock is available or not. And again, this is not how SQS actually does it. The locks are handled on the SQS side. This is just for us to understand the places where we can implement this. SQS broker becomes a very easy use case to help us understand where does this fit. You can have another great example which Sarthak gave to ensure that we are not running multiple things we are not running the same thing multiple times is another use case of it. You can implement a whole lot of things using central logging system, right? So wherever you would want to have distributed coordination using logs, this is what you would be using, or the implementation of it would be very roughly similar to this. Any other question? We are almost done. Okay. Another use case for this is logs across multiple MongoDB shards for multiple documents updated within the same transaction, right? So MongoDB says na ki we are ACID compliant. How it is ACID compliant, right? When we saw with database sharding, right? All the operations within that shard, we basically when we shard, we say that the request has to go to this one shard only, right? And that is ACID compliant. So wahan pe anything which is running, it won't be, so it has to be ACID compliant, right? Because all the requests is about that is only going there, and you can't have cross shard joins in terms of SQL. You can't have cross shard transactions and all. But MongoDB gives us cross shard transactions. How does it give us? It uses distributed lock. It has its own lock manager. So within the same transaction, when the documents are updated across multiple shards, it has to acquire a lock on the documents which are updated, right? And that lock is taken remotely on a remote lock manager. And that is how MongoDB ensures cross shard ACID compliance. And that is why they are terribly slow. That's exactly what they have written in the documentation. It is not recommended to have a very heavy ACID system or very high throughput on distributed transactions, because this is exactly how they have implemented. Right. So locks ensure that other transactions do not update the same document. So they take locks on what? Document ID. So here in Redis, so let's say if you were MongoDB developer and let's say you are using Redis as your thing to do the lock management. So instead of Q7, what would you have? You would have collection : document ID as your key, and your transaction ID as your value key. Who holds the lock for this document, right? Under this collection, this is the document ID, and this is the transaction who is holding the lock for this document. And that's how you would have like a coordination for a transaction spanning multiple shards through a common lock manager, which is remotely set up. Yes, Anshuman?
Yeah, so I was just thinking, so there can be some corner cases, right? What if Redis goes down?
That That's why you would have to have durability. So that's why you would use Redis when you are okay for your data to be lost. Typically, your distributed locks are taken on Zookeeper, which is persistent, rather which is durable. Right? Even if it goes down, it comes back. The locks are intact. So Zookeeper becomes a great use case for having a distributed lock or a remote locking system.
Okay.
Next assignment. Implement and simulate. This is important. Be hands-on. If you're not hands-on and if you're just doing theory, it won't be fun. Be hands-on, implement or rather simulate distributed transactions. Again, it is as simple as the way we implemented load balancer. Just have two dummy Flask server running with just one API, having a normal time.sleep, which mimics the behavior. Like if you want a broker to simulate, just have an in-memory queue, like doing a queue.poll. That API does a queue.poll and gives you the message out. Like you can simulate a very simple SQS sort of stuff with a local setup and see how to build distributed transaction, have a Redis setup running. And then obviously once you have a base setup running, try to apply load and see how the coordination happens. Right? It's a very easy to implement, hardly 5 hours work if you're doing it for the first time, but do it. You would get a very, very, very in-depth understanding of central locking, and you would be very happy, obviously, by knowing it. I've implemented something around this, and obviously, once you have a deeper understanding, it's easy to pick it and apply it at your workplace, or if you are preparing for interviews, then for interviews. Okay. SQS architect, something, and a few things that you can also implement is visibility timeouts and message expressions. Do a brainstorm about it. What visibility timeout does and message expression does, Google, and then implement that one, because that also requires to some extent remote locks. And in that remote locks, you might need to set few parameters here and there. So that is very, very, very important. So do that one. And there is a great article on distributed locks. So up till now, what we discussed was remote locks, and there is another concept called distributed lock. So instead of having one lock server, where up till now we were discussing about like one Redis instance there, instead of having one Redis instance, we want things to be distributed. So having 5 or 7 Redis nodes, and there we we set up consensus key who owns the lock and what. This is where distributed locks come in. So one Redis server is unable to cope up. So you scale that system up having multiple Redis servers. So that is where distributed locks come in. There is a great article by Martin Kleppmann, the author of the book Designing Data Intensive Application. He has written about distributed locks on Redis. This is the exact title of it, or rather deadlock detection in remote locks. You can read this. So read this stuff and you would understand how to have distributed locks. We would cover one algorithm called Redlock around it. It is loosely based on distributed locks on Redis, but a critical one to understand. So with distributed locks with Redis, the algorithm is Redlock. It's very popular. Almost everyone who uses distributed locks with Redis, so they typically use central locking. So basically, distributed locking with one lock manager is central locking, right? So most of the companies typically use one Redis server, and they use library called Redlock. And basically, this is exactly the name of the algorithm. They use this to have distributed lock implemented in their system. So here, Redis acts as a lock manager. It gives you safety and liveliness. The idea is very simple, right? Every single of this thing is very important. Like what happens is every command of Redis is atomic. So to acquire a lock on a single instance, this is what you would fire. Like we were discussing like Q7 consumer one, but how do we actually invoke it? We invoke it like this: set space resource. Resource is what? On which we have to take lock, which is Q7. Client ID, who is taking the lock, which is consumer one. NX is something which is specific to Redis, which says that when key does not exist, okay, then only this set should happen. So this is like conditional put. Okay, then you do a PX of 30,000. So PX gives us the expiration key, TTL after 30,000 milliseconds. Yeah, it's in milliseconds, right? So after 30,000 milliseconds or seconds, mostly, I'm not sure. Need to check ki kaun si unit hai wahan pe, right? So something around it. So this is the expiration time. So if this key should be automatically deleted after 30,000 units of time. Mostly milliseconds it should be there. Okay. So this is how in one Redis command you can acquire the lock on a single instance. Now to release the lock, what we have to do is we do a get. We get the lock on this. Now we know that lock exists. We get the lock on it and we delete only when the value that we got is same as current client ID. So that I don't accidentally delete others' lock. Right. So this ensures that the one who acquired the lock releases it. This is a very critical thing. This was something that was asked to me in one of the interviews, and I did not mention this, and I was rejected solely by this. It was given me in the feedback. You didn't consider this. You just said, I just said, Array, I was just too young there. I said, I would just get the key from the Redis and delete it. And he said, any other edge cases? I said, no, I would just get the key and delete it. So it was obvious to me that I would be deleting only if I acquired, but being very explicit about it, yeah, I would do that check. If the acquired, if I'm the one who is owning the lock, then only I would be deleting it. Right? Like this is something that most of the people forget. That's why just putting an extra stress. So you would be deleting only when if the value that you got is same as your client ID, which means you are the one who is owning up that lock. Right. So now what would happen if we do not get before delete? If we are directly deleting it, so we are typically deleting, we may delete the lock held by other, which is what the concern is. And now we would be making this thing distributed. Varun, I'll take question at the end. Let me just wrap up this thing, just only four pages more. Okay. So this is where the distributed part comes in. So instead of having one server or one Redis server, to make it distributed, we add 5 nodes of Redis. All are independent, no replication, right? Because that's when you are scaling. If you are, if you are not doing this part, if you are replicating, then how are you even making it distributed, right? So they are not coordinated. They are all independent, 5 nodes. Acquiring the lock. So this is a classical distributed systems algorithm, right? Where to ensure that you have acquired the lock only when you get the majority out of it. So client goes through all 5 masters sequentially to acquire the lock. Okay, with some timeout. Right, and if you don't have timeout, then the problem hai. So there are just edge cases that you do, and this very based on the Martin Kleppmann's blog. So if you want to go very deep into, not very deep, but still want to have detailed understanding, anyway, I would recommend going through that. There are few edge cases that he has covered, which I have not, because anyway you would be going through that. Right. So what do you want to ensure is when acquiring the lock in majority of the Redis instances, the lock has to be taken under my name. I have to ensure that, right? That only I know that I am the owner of the lock. Otherwise, I'm not the owner of the lock, right? The lock needs to be acquired on the majority of instances. So 5 ka majority is 3. So on 3 instances, the lock has to be under my name. Then only I'll say that I own the lock. Otherwise, I don't own the lock. If the lock acquisition failed, then client goes to each master and deletes the key. Basically, if I fail to acquire the lock, let's say I found only 2 instances having the lock on the same entity, I would be going ahead and deleting the key. Anyway, TTL is there, but if I'm proactively deleting it, I'm just making system faster, right? So obviously partially acquired lock will be cleared on that, like on 2 instances I've done that. So it would help us basically clean up the things that we are responsible for. So this is how acquiring the lock would look like, right? So majority hai, then you have acquired the lock, otherwise not. So you are literally going through 5 of the systems one by one and doing that part. I would say ki, why do we need distributed locks? So when do we do that? Distributed lock when we are unable to cope up with the scale of the system. So you might want to, you are using just multiple brains to acquire the lock. So your key might not be stored on all 5, but even if it is stored on 3, you would say that lock is there, right? And since there is no replication, so it might happen that your key might not even be stored on other 2 Redis nodes, right? It's stored in 3, you are done, you have the lock, you can skip it. So this is where you can attain a bigger scale of it. So this is what the flavor of distributed systems look like. So having redundancy. So even if one of the nodes fail, like your things would not, like in the single node thing, what was the problem? As someone pointed out, if the Redis server goes down, like, so your things are volatile in memory, it broke, right? So a solution for that is to make it distributed. But when we make it distributed, we need consensus. To need consensus, this is what the acquiration flow would look like, right? This solves the problem of having a single point of failure as a lock manager. So this ensure that our lock manager, I'll just write here, our lock manager is not a single point of failure anymore. Correct. With the 5 setup, this has ensured that my lock manager is not a single point of failure. Even if one of the node goes down, it just ki thoda sa lock ka idhar udhar ho jayega. But obviously my data is not lost because majority wins, right? So this is where the critical thing lies in, where I have just removed the single point of failure in my system, right? So any question for this implementation of this red lock algorithm? And obviously, why do we need distributed locking? Anshul, I see your hands raised. Was it for the past one or current one?
Yes.
अच्छा पास हो चलेगा ठीक है So when do we use distributed locks? We use it when you want to lock a common resource spanning multiple processes or services. By adding multiple nodes, we eradicated single point of failure and attained a bigger scale. Locks enable coordination across multiple systems. A great example of this would be, the 2 examples that we took, this same as that, right? Multiple services trying to acquire a lock on the same item, like 2 services, 2 transactions on same entity, like MongoDB, 2 transactions trying to update the same entity, right? Same thing, right? And the final thing, what you should definitely go through is Chubby. Chubby is the name of the paper. Chubby, Lock Service for Loosely Coupled Distributed System. This was the first paper I've ever read in my life. This was the first paper. and it basically strengthened my understanding of distributed locking. So do read this Chubby lock service for loosely coupled distributed system, and you'll get a very detailed, deeper understanding of locking. And obviously, everything is based around the same logic, like having redundancy to ensure that there is no single point of failure. That is why you need multiple nodes. But how do that coordination happen? How to gossip things and all? That is something that would that is part of Chubby, and it's very simple to implement if you have time. I would not recommend you to implement this, but if you have time, interested in implementing it, very easy to implement. It was one of the assignments given during my BTech time, so it's a very simple one to implement. I did not do it at that time. I was not, I did not know how to code well. I just copied it from the internet. But yeah, if given a chance, I would definitely love to implement it. So Chub is something that if you would want to implement, you can go ahead and implement it. But otherwise, do give this paper a read. And this concludes distributed locks and distributed systems in general. Any questions? No? So, nice. I hope you guys understood and not slept. Yeah.
Maybe we'll have questions next time because this
Yeah.
topic somewhat, right? Yeah, there was too much of a new stuff. Yeah.
That could be, see, system design is really very massive. You can't just, if you just focus on one, there will be so much of other things that will be left out. But I've tried to cover a lot of things in depth. Why this? Every single why I've tried to answer. Why do we even need to have multiple Redis nodes and all of those parts, which is typically not available on the internet with ease. So I just try to cover that. Yeah, Rahul.
Sorry, I was in. So, how do you actually implement connection pool?
How to implement connection pooling?
So, do we have like a prerequisite request making to server? And what if like a server changes, as you know, like Amazon is
Your
doing
server
payment?
died up. Okay. So in that case, all of those TCP connections automatically are aborted, and you would know that TCP connections are aborted. You would try to create new connections on that. Okay. The way connection pools are happened, there are two ways to do it, or rather two phases of doing it. First is pre-warming the TCP connections, where let's say you create a pool of like, let's say 10 connections every server, and you keep it ready. And then other connections are created on demand. So first you try to utilize those 10, and then if you require more connection, it is created and then it is added to the pool. How the connection is added to the pool? Because the TCP, see, once you have received EOF, okay, once you've received EOF, you know that your job is done, right? Once your IO call, once your system IO call is done, it means the data transfer is done, right? But your TCP connection is not .close is not invoked. If you don't invoke .close, the connection is not closed. So that's when you just add the object reference into a pool, and that's exactly how you would implement connection pooling.
What is actual data store for connection pool? It's just
array, normal array. You can actually use a priority queue to make this thing efficient. So you can use a heap to do it, or anything that gives you, order one access to any one of the connection, like order one access. That's what your criteria is. So you can use array and an index that gives you like done. But basically queue is a proper data structure which you can use it. So vector, queue, anything that gives you order one access, order one insertion, order one delete. But to some extent, order one insertion, order one delete is something that you should be using for this.
And the last one, so you mentioned you'll be telling us the last, how do you implement circuit breaker in your past?
Circuit breaker, na? So what did we do? We added in Redis, we added for every service, if this service is alive or not, right? So depending on whatever it is, or rather, let's say I have, we'll take a real example. So I have a service called profile, right? And this service is something that is not doing well. Now, if this service is not doing well, now what I would do is, let's say my service is communication, and I use profile to get the person's first name, last name, so that I can create a personalized message for him or her. So given this thing, my communication is running on a Redis database, which has our configurations. And for this configurations, what I have is I have a key like call_profile, and it is set to 1. Right? 1, I have to do circuit breaking. So circuit breaking for me or for both the startups I work for, it was manual, because you apply circuit breaking not as an automatic remediation, but as a step where you are manually trying to delete, or where you're basically manually trying to protect your system from going down. So since this is manual, what we do is we just have one dashboard, which may we say key for my service, do I have to call profile? I just set this 1 to 0. Right now, it takes about we have a refresh time of 50 seconds. Okay. So once every 50 seconds, we make an API call to Redis to fetch the latest value of configurations. Right. So worst cases, for 50 seconds, I would still be making call to my profile service. But after 50 seconds, once I receive 0, I won't be making any calls to it. Right? As simple as that. We just use Redis because my communication service or any service, typically uses Redis for some of its use case. So we have stored this information. Once every 50 seconds, we keep a polling. So basically, this is the poll interval to which we fetch the fair set of configuration out of it. First, and this is exactly how we have implemented circuit breaker.
And so you manually modified the Redis set get thing
Yes.
to 1 and 0.
Yes. This can be very easily automated, but very if we have to automate it that frequently, which means our systems are very much fucked up because so many things are going wrong then. Right. So that's why we did not think of even automating it, right? Yeah, Anshuman?
So if you could go 2, 3. Okay, Anshuman.
Yeah, you can ask your question. I'll ask later.
I was saying that I just wanted to have one more sort of basic understanding on 5 masters, and then you said we have 3 things, right?
Why? Because a majority, like out of 5, you need, if you have taken, so if your key is set only in 2 of them, which means someone else has taken a lock on that. Correct. So if so out of 5, I need to have my key set in at least 3 of them. Otherwise, I don't have a majority.
So here my key, the lock is being set into basically 3 servers.
So I'd be calling set on all the 5 masters one by one. Okay. Now my set call, which is this particular set command, would succeed, right? So because this command would either succeed or fail. This command would fail if the key is already set. Correct? Because this NX would ensure that my command would succeed only when the key does not exist. Correct. Now, go on.
Okay. So that is okay. So, but what are the situations where we need a 5 master setup, and then we are?
So this is typically
the lock manager.
Any odd number. You can't have an even number because उसमें majority नहीं निकलेगी. Right.
Got it.
So 3 पे, so 1 से 3 पे जा सकते हैं.
So when would we need to scale a lock manager to from 1 to sort of a 3 or?
To avoid single point of failures. So,
but for that we'll have a replicas, right?
Right?
You can and then replicas would.
So you can have replica that can be promoted. Another approach is to have this part. So there are multiple.
Okay, but managing multiple masters is again a big headache, right?
No, because
active.
These are all independent. So you don't have to do replication amongst them.
Oh, okay. That way.
Right. So I've written no replication or coordination is required here. which means
Oh,
these are independently
fine.
set up. So you are anyway paying for that backup replica, right? But then if this master goes down, the other one takes its place, versus if one of the master due to any reason goes down, your system remains unimpacted.
Okay. And here the timeout that we have set is like if a particular service which has taken the lock and it doesn't finish
Release the lock. Yes.
release the lock in that time frame, then
Correct.
it will automatically.
Yeah.
Yeah. Okay. Yeah. Thank you.
Thanks. Yeah, Anshul.
Yeah, I have a different question. So I was wondering if on the Prometheus data, is it possible to do some kind of data science? I mean, I know that there is an in-memory DB
Prometheus
for
just
Prometheus.
stores the data. It's a time series data, right? You
Yeah.
can leverage it however you want, however you'd want to. If you want to build an anomaly detection on top of it, it's your logic. You would have to pull data out, and let's say for every 1 minute or something, or let's say you're analyzing data in a window of 1 minute and finding out if actually there's an anomaly or not, right? But basically that would be your logic around that. So the database does not give you any such things out of the box. It's a pure
Oh,
database.
Okay. Is anything available right now? I mean, I'm not
There
sure.
are libraries that run on top of this database. Obviously, there are libraries, but basically there is nothing that comes out of the box for it.
Okay. Yeah. Okay. Got it. Okay.
Yeah, Sanjay.
Yeah, I just want to share my experience with this
Please.
distributed locking. So yeah, mainly this thing about we didn't use that lock, we used another algorithm called Paxos. And what we found was that like it only gives you a small window for single point of failure. Like even if one node goes down, right? Then what we started seeing is that a lot of the clients started to get nobody used to get a majority, and then they used to keep retrying, right? So that's like more like the cascade sort of thing. And then what happened is it put a lot more pressure on the other nodes, and eventually they would also start failing. So all it does really in reality is that first of all, adding more than 5 nodes is incredibly hard, and the other thing is that if it just gives you a small window, if that node doesn't recover within that short window, then there's a very good chance that your entire thing goes down as a whole. So it's not like horizontally scaling where you can just add more nodes because of this majority problem, right?
Yes.
You will that problem is also there. So that's why consensus is a bit hard that way.
Exactly.
Yeah.
So you implemented Paxos on top of any such database out of the box, or basically was it a pure or how was the implementation detail of it?
The Paxos was written in Erlang, which is on top of a Postgres database.
Postgres database. Okay.
Yeah. So yeah, but that was fine. But again, this problem was we found it to be very sensitive against even if a single machine goes down, within a short amount of time, the entire system would not. Nobody was able to take a lock.
Because four nodes okay, basically the nodes became even. Once it becomes even, so majority in a system which is having a very high which are having a very high transaction load, it won't be possible.
Yeah. So we need to have good circuit breakers there to give that. It cannot just be nodes going down. The other thing is partitions, right? That node may actually be up, but he's not able. Nobody's able to reach that guy. So yeah.
You got distributed systems is extremely complicated, and this typically happens at scale. If you're running things locally and all, or having a very minuscule scale, this sort of errors won't even actually pop up, right? But once you start attaining that scale, that is exactly where you would, everything that you have read in theory would go bad in practical when you at scale. Nice. Thanks, Sanjay, for sharing that. Yeah, Umang?
So on the Amazon's Aurora DB part, you told basically the read replicas would be automatically handled by Aurora. So like, does it use a load balancer implemented inside of Aurora, or is it something else?
Implementation detail I don't know, but it has a common read endpoint, and behind that you can have as many read replicas as you want. So you can on the fly add read replicas to it.
Okay, and like how efficient would be using a DNS based routing solution instead of using like Aurora or any other DB which might be like that. Like basically read replicas would be some set of IP addresses, right? We
And
can
both are exactly the same. See, the implementation won't vary much.
okay,
And
and
it's
on the trade-offs part, just on the trade-offs part, wouldn't be there any
I
trade-off of
don't think so. There would be any major trade-off. It's just that यहाँ पे you would have to have another load balancer that is sitting आगे थोड़ा सा.
got it? Yeah.
But obviously, but my answer might not be correct here because I don't really see a huge difference here or there.
Yeah, no, as in yeah, obviously it is a managed solution, so would be better.
DNS level things, DNS doesn't have major metrics, right? But load balancer will have metrics on the back end. So I believe the load balancer one will actually better.
Yeah, great point, because you would get those metrics. Nice, great point. Thanks.
So metrics about status health or something else?
Yeah, status of the backend machine.
Okay, no, as in there were products around it too. So that's why, like, which gives you that capability. So maybe I think Route 53 also has some of those capabilities.
No, but here, like, let's say these are databases behind it. So you might want to have how many SQL queries were fired, which resulted in this much of time or something like that.
Okay, yeah, those kind
of those metrics in real time that are flowing through that is very evident for load balancer, but not so for route.
Got it, right.
Yeah, but one question of this topic. So we discussed about API gateway and load balancer, right? So when would one specifically use API gateways and go for a load balancer instead?
API gateway, see, load balancer does not have fancy features which API gateway has. API gateway you can cache very easily. You can configure complicated rules. Okay, load balancer it's very simple. So using a custom load balancer, you can implement a functionality like API gateway. So API gateway is nothing but a fancier load balancer. Okay, but the job of API gateway is to act as that interface which forwards the request to services. So those services ke load balancers, like that is one of the use case. Another use case of an API gateway is where you have a service mesh instead of having a few dedicated load balancer for each service, having a service mesh, something like an ISTIO, if you have heard of it. Like that is where API gateway plays a very interesting part. Third, API gateway plays a very important role as compared to load balancer because it does not assume that the systems behind the load balancers are homogeneous. API gateway pe you configure the rules ki where does this request or basically if my request matches this, it should be forwarded to this. If my request matches this, it should be forwarded to this, because it assumes that systems behind my API gateway are heterogeneous. On the other hand, for load balancers, they assume that systems behind my load balancers, they are all homogeneous, which means I can forward the request to any one of them.
So it will be like API gateway, then load balancer, and then homogeneous set of backend.
This is typically set of how you would have key API gateway might forward request directly to a load balancer. Yeah. So right now, like at Unacademy, we are transitioning from monolith to microservices, and we have used API gateway exactly for this use case. So API gateway, we have very recently forked out one of our services. So request for this service has a specific route pattern. So in API gateway, we have configured that route. This route should go to this load balancer, while other things should continue to go to our legacy load balancer. And then slowly and steadily, we would fork out other services out of it and use this API gateway as our intermediary, right? And then once the monolith is entirely split into microservices, we'll be deleting the monolith altogether.
Okay, and then same applies to API gateway configuration. Like we'll have to have a vertical scale.
Correct. And with API gateway, you get caching out of the box, you get authentication out of the box. So those fancy application side features, you can get that. So like API gateways caching is much more efficient versus your application level caching, because now it is dealing with pure responses. So you will have one more layer of caching which you can use instead of even going to your API servers and then hitting the cache. Your API gateway can immediately serve the request from the cache, basically from the cache.
Okay, so when we say caching, so like a user profile. I'm getting a user profile. So
yeah. So it would not really have to forward the request to load balancer. From API gateway only can serve the response.
Okay.
I want to have a bird's eye view on the complete architecture. So there will be a DNS entry. It will come to the load balancer, and load balancer will have a lot of API gateways in the backend.
No. DNS entry from DNS to API gateway to load balancer to API server.
Okay, but API gateway provides the load balancing functionality as well, is it?
So it might have multiple implementation of, it might have multiple servers within it.
Okay.
Chala. Awesome. Thanks, guys. Tomorrow we'll be diving into distributed ID generators. We'll only be discussing ID generators only. And if we still have time remaining, we will be. So then I'll be opening up for the question and answers like always. If you have any questions, just keep adding it. So we'll have a couple of sessions where we would just a couple of second half where we would be discussing questions or experiences or that sort of stuff. Okay, but tomorrow's agenda would be distributed ID generation. That's it. So how a lot of different companies have implemented ID generation and what are the pain points there, right? So through that, we'll be finding out very interesting high level patterns around systems that we are building. Yeah. Awesome. Thanks a ton, guys. See you tomorrow.